Hello there, and welcome to the Sleepy Science Channel. If you enjoy calm, carefully explored science that helps you unwind while gently expanding the edges of what you know, please take a moment to like the video and subscribe to the channel. Your support motivates us to continue creating more meaningful videos. And before settling in, dim the lights, get comfortable, and let your mind wander through the calm universe. Tonight, we're going to drift into one of the biggest questions of scale a human can ask. How large is the universe when compared to the galaxy we call home? It's a question that already carries its own sense of size within it. And yet, no matter how many figures or measurements we hear, it always seems to overwhelm the imagination. We exist inside something unimaginably vast. But we also look outward into something even greater. And tonight, I'd like to gently walk through that difference with you. Before we begin, I'm curious, where in the world are you listening from right now? Maybe you're in a city where the stars are hidden. Or maybe you're somewhere rural where the Milky Way stretches clearly across the sky. Perhaps it's late and you've settled into bed. Or maybe it's a quiet afternoon and you're just taking a moment to pause. Either way, you and I are sharing this moment, and that's a small wonder in itself. If you find this kind of calm exploration helpful or soothing, I'd really appreciate it if you liked or subscribed, so others who might need a quiet voice to follow can discover it as well. Now, take a slow breath, settle back into your chair or your pillow, and let's begin to think about what it means to be small in a universe that seems determined to be endlessly vast. It helps to imagine yourself outside for a moment. Picture a clear, cool night, the air completely still, and above you, the sky wide open, filled with scattered stars. Maybe you can see just a handful because of streetlights. Or maybe you see thousands. Each one is a point of light from another sun, many of them with planets circling, and all of them belonging to something bigger. When you look upward, you're not just seeing stars scattered randomly. You're seeing part of a vast structure, a spiral galaxy, the Milky Way, that holds those stars together in a loose but definite pattern. It stretches so wide across space that even traveling at the speed of light, you'd need tens of thousands of years to cross it. And yet, for all of its immensity, our galaxy is just one among billions, perhaps trillions, inside the universe. It's easy to speak in those numbers, but what does it actually feel like to compare them? Tonight, we'll try to take that measure step by step, always remembering that while the words sound huge, they are still just signposts pointing towards something our minds can only barely begin to picture. When you stand beneath the stars, it can be tempting to think of yourself as tiny, as though the great cosmos is stretching endlessly in every direction, and you're just a dot upon a dot fading into the background. But there's another way of looking at it. You are part of the galaxy. You are part of the universe. The same atoms that formed inside stars billions of years ago are here right now in your body. The space above you is not separate from you. It is continuous with where you are sitting. The floor beneath your feet, the air in your lungs, the warmth of your skin, all of it is connected to the same universe we're about to measure. So instead of feeling small, you might also feel included, woven into the scale of what we're describing. As you let that thought settle, consider how unusual it is that we can even ask a question like this. For most of human history, the universe was the dome of the sky.
and the galaxy was not even known to exist as a structure.
People looked up and saw stars, sometimes a band of light across the heavens. But the idea that all of those stars were bound together in one great disk, and that the disk itself was only a piece of something far greater, that's a very recent realization. A century ago, astronomers were still debating whether other galaxies even existed, or whether everything we could see was contained within the Milky Way. Now we know that the Milky Way is just one island among countless others in a cosmic ocean. In that short time, our sense of size has expanded by a factor that is hard to put into words. That expansion of awareness is what we'll explore together. Think for a moment about distance in your daily life. A few steps to the kitchen, a walk around the block, a drive to another city, a flight across an ocean. Each of those scales feels tangible. You know what an hour in a car feels like. You know what a long-haul flight feels like. But when we begin to compare galaxies and universes, the scales grow so far beyond human experience that words like mile or kilometer become almost meaningless. Instead, astronomers reach for light years. The distance light travels in 1 year. Light, the fastest thing we know of, covering nearly 10 trillion kilometers in 12 months. And even then, that measure struggles to keep up with what we're describing. Our galaxy is about 100,000 light-year across. Already, that is a number that resists visualization. But compared to the universe, which stretches more than 90 billion light-years across in observable terms, it is just a single step on a staircase that seems to go on forever. This is where the imagination comes in. Tonight, we'll take it slowly, letting each number breathe, letting each comparison unfold without rushing, so that instead of becoming lost in a blur of statistics, you can build a kind of mental landscape. You can place yourself within the galaxy, see how wide it is, then compare it to the clusters of galaxies around us, and finally, to the observable universe. By the end, you won't have a perfect picture. That's impossible. But you will have a sense, a gentle awareness of the relationship between our home and the wider cosmos. That's all that's needed for now, because even a hint of that scale is enough to leave the mind both humbled and soothed. Take another slow breath, and let's stay with that image of being under the stars. Notice how they twinkle, how some are brighter than others. What you're seeing is just a small fraction of what's really there. In fact, from most places on Earth, only about a few thousand stars are visible to the naked eye. But our galaxy contains hundreds of billions of stars, most of them hidden from our eyes. Imagine multiplying the night sky you see by a factor of 100 million. That is closer to what the Milky Way actually holds. And then imagine that this entire collection of stars, gas, dust, and dark matter is just one galaxy among countless others. It is the difference between a grain of sand and a beach, between a single page and an entire library. The numbers become so large that they can almost feel comical. But here we are, sitting comfortably asking the question, letting our thoughts drift across those scales without needing to solve them, only to feel them. It's worth pausing here to reflect on why this question is even soothing at all. Usually, when faced with something impossibly large, the instinct is to feel overwhelmed. But in this case, the opposite often happens. Thinking about the galaxy and the universe can be strangely calming because it puts daily concerns into perspective. The stress of a small task, the worry of a single moment, seems to shrink against the backdrop of billions of stars and trillions of galaxies. It doesn't mean those concerns don't matter. They do deeply, but they are set inside a larger frame, and that can create a sense of balance. You're not the center of everything, but you are part of something that includes everything. In a way, it's a reminder that there is space for you, literally and figuratively, in the grand structure of existence. Now, let your mind wander back to the Earth beneath you. This planet is our starting point, and from here we'll lift off in our imagination, first into the galaxy, and then beyond. Earth itself is about 12,700 kilometers across. That's a number we can picture more easily. A few hours in a plane, and you've crossed a continent. A day in orbit, and you've circled the planet. But scale it outward to the solar system, with Neptune orbiting nearly 5 billion kilometers away, and Earth already begins to feel small. Then place that solar system inside the Milky Way, stretched across 100,000 light-years, and the solar system itself becomes a point too tiny to notice. And then compare the Milky Way to the universe, which spans at least 90 billion light-years across, and the galaxy becomes a point as well. This chain of scales is what makes the comparison so striking. Each level is its own world, and yet each one becomes small within the next. And this is only the beginning. For now, though, we're still standing beneath that star-filled sky together, just starting to ask how everything fits. The night is still, the air is quiet, and the idea is simple. The galaxy is vast, but the universe is vaster still. When we think about where we live, we often stop at Earth, sometimes reaching a bit further to the moon or the sun. Beyond that, it starts to feel abstract, as if it belongs to something entirely separate. But the truth is, our real home, the place that holds every star we see at night and every planet we've ever imagined, is the galaxy. The Milky Way isn't some distant structure outside of us. It's the structure we're already inside. To talk about the galaxy is to describe the stage on which our entire solar system exists. Even a small understanding of it is like understanding the shape of your home, instead of only describing a single room. Tonight, let's take our time to look around inside this home, to notice its features and scale, and to place ourselves within it in a way that feels grounded and calm. If you could step back far enough from Earth, away from the clutter of our atmosphere and beyond the orbits of the planets, you would eventually see the Milky Way revealed. From within, on the surface of Earth, we only catch glimpses of its true shape. The hazy band of light that stretches across the night sky on clear, dark evenings is our edge on view through the disk. But from outside the Milky Way is a spiral galaxy, a flattened disk with sweeping arms curling outward, dotted with stars, nebula, and clusters. At the center lies a dense bulge, a crowded sphere of stars orbiting a supermassive black hole known as Sagittarius A. The entire structure is laced with dust and gas, glowing faintly in wavelengths we cannot see with our eyes. To describe it in simple terms is easy to imagine standing outside, and looking back is harder. But even if we cannot truly picture it, we can place ourselves within its outline and begin to get a sense of our location. The disk of the Milky Way is about 100,000 light-year across and roughly 1,000 light-year thick. Inside this disk, stars orbit the center like a great whirlpool. Our solar system is located not in the crowded center, but out on one of the spiral arms known as the Orion Arm or Orion Spur.
about 27,000 light-years from the core. That distance alone is hard to absorb. Light, moving at the fastest possible speed, takes 27,000 years to travel from the center of the galaxy to us.
That means, when astronomers observe the central region, they are looking not at the present, but at light that left those stars long before human civilization began. We live in a galaxy that contains its own deep history, simply by the way light moves within it. It's worth pausing here to think about what it means to live inside such a disk. The night sky we see is not random. It is the view from one particular spot in the galactic neighborhood. When you look toward the thick band of the Milky Way, you are looking into the plane of the disk where stars are crowded together. When you look away from it, the sky seems thinner because you're looking out of the disk and into the more sparsely populated halo of stars that surrounds it. Every direction you turn is still inside the galaxy, but the density changes with your line of sight. In a way, every stargazer is like someone standing in a forest. Look along the path of the trees, and the trunks seem close and endless. Look upward, and the gaps appear wider. The forest is the same, but your perspective changes. Our galaxy is like that. Only the trees are suns, and the forest stretches for tens of thousands of light years. Inside this home, there are features as distinct as mountains or oceans on Earth. There are globular clusters, tight knots of hundreds of thousands of old stars that orbit the galaxy like satellites. There are vast nebulae, clouds of gas and dust where new stars are forming, illuminated from within by glowing hydrogen. There are supernova remnants, the husks of exploded stars scattered like cosmic fossils. And weaving through it all are the spiral arms themselves, regions where stars and gas are more densely packed, winding around the core in gentle arcs. Our solar system moves with the disk circling the center once every 230 million years. That means in the time since the dinosaurs walked the Earth, our solar system has completed just one orbit of the galaxy. Each lap is unimaginably long on human timescales. Yet the galaxy itself has existed for more than 13 billion years, completing dozens of such rotations since its formation. We live in a place that is not only vast in space, but ancient in time. The supermassive black hole at the center, Sagittarius A, deserves special mention. It contains about 4 million times the mass of our Sun, compressed into a region no larger than the orbit of Mercury. It is invisible to the eye, but its influence shapes the orbits of stars in the core. For decades, astronomers tracked the motion of those stars and confirmed that only a black hole of immense mass could explain their speed. In 2022, the Event Horizon Telescope collaboration released the first image of the region around Sagittarius A, showing a glowing ring of hot gas circling a dark shadow. That shadow is the closest we could come to seeing the black hole itself. Knowing that such a monster sits at the center of our galaxy is both unsettling and/or inspiring. But in a strange way, it also makes the galaxy feel more like a living system, with a beating heart hidden in its core. Around the disk and bulge lies another component, the halo. This is a roughly spherical region extending far beyond the visible disk, containing scattered stars and globular clusters. More importantly, it is thought to contain vast amounts of dark matter, an invisible form of mass that does not emit light but exerts gravity. Without dark matter, the stars in the outer disk would not orbit as they do. The galaxy would simply fly apart. Instead, unseen matter provides the glue that holds the structure together. In this sense, the Milky Way is not just what we see, but also what we cannot see. A reminder that our picture of home is still incomplete.
So far, we've been speaking in terms of light years and billions of stars.
Let's slow down and anchor those numbers a little more. Our Sun is just one among perhaps 200 to 400 billion stars in the Milky Way. That range is large because it's difficult to count stars hidden by dust or faint with age. But even the lower number is staggering. 200 billion suns, each potentially with planets. If only a fraction of those stars have habitable worlds, the number of possible places for life in our galaxy alone is enormous. And yet, despite this abundance, the stars are spread so widely apart that the nearest to us, Proxima Centauri, is more than 4 light-years away. Even if our galaxy is filled with life, the distances are so immense that neighbors would be difficult to reach. The Milky Way is crowded and lonely at the same time. A city of lights with streets so vast that every home feels alone. As that idea settles in, think again about standing beneath the night sky. When you see the faint band of the Milky Way, you're looking along the edge of the disk, your view passing through thousands of light years of stars. That perspective is only possible from within. From the outside, you would see the full disk stretched through space, slightly tilted, glowing softly. Astronomers can't leave the galaxy to capture that image. But by observing other spiral galaxies, they piece together what ours must look like. In a sense, every image of another spiral galaxy acts like a mirror, reflecting what our home might appear to be if we could step beyond it. Those pictures, taken by space telescopes, revealed graceful structures, arms filled with blue stars, dust lanes curling like smoke, and bright regions where new stars are being born. They are beautiful, but their greatest gift is that they let us imagine the shape of the place we live. This is not just idle wonder. Knowing the size and structure of the Milky Way is essential if we want to place it in the context of the universe. Only by measuring our home can we begin to compare it to the scale of the cosmos beyond. Astronomers have used a variety of methods to map the galaxy. They measure the motion of stars, trace the distribution of gas, and use radio telescopes to peer through dust. The Gaia mission, launched by the European Space Agency, has mapped the positions and motions of more than 1 billion stars, giving us a 3-dimensional picture of the Milky Way with unprecedented detail. With each new observation, our image of home becomes sharper, but the vastness of it ensures that mysteries remain. Even now, the far edges of the disk and halo are only faintly understood. The more we know, the more remarkable it becomes that we are here at all. Our solar system orbits quietly in the Orion Arm, far enough from the center to avoid the dangers of dense star clusters, close enough to see the richness of the disk. It is a location that provides stability, sunlight, and a view of the night sky that inspires questions like the one we're asking tonight. To live inside a galaxy is not unusual. Every star belongs to one. But to be able to describe it in detail, to measure its size, and to compare it to the wider universe, that is a gift of both science and imagination. As the thought unfolds, notice how the scale of the galaxy begins to feel more comfortable. At first, 100,000 light-years may sound overwhelming, but once you place the solar system within it, once you imagine the arms, the bulge, the halo, and the central black hole, it begins to take shape like a map of a city. You know where you are in relation to the center. You know the direction of the arms. You know that the disk spins slowly, carrying everything with it. You know that the night sky is your local neighborhood, seen from within. With that knowledge, you can begin to ask the larger question. If this is our galaxy, how much larger is the universe beyond it? But before we drift further outward, let's stay here a little longer in the vast night of our galactic home, letting its shape and age sink in. The Milky Way is not just a background. It is the place in which we live every moment of our lives. Its gravity holds us. Its stars give us light. Its arms provide the structure of the sky. To appreciate its scale is to feel both humbled and sheltered. This is our home in the vast night, and knowing that makes the step outward into the universe even more meaningful. When we talk about the Milky Way, it is easy to slip into the habit of calling it our galaxy, without pausing to think about what that word really means. Galaxy. It is one of those terms that feels familiar, something you might first hear as a child when someone points at the sky and tells you that the stars all belong to the same vast collection. Yet, if someone were to stop you and ask directly, what exactly is a galaxy? The answer is not as simple as it seems. It is a word that covers something both straightforward and profound. Something that can be defined by physics, but also understood only by stepping back to imagine what space itself looks like on the larger scales. Tonight, let's take our time to unpack that question, not with the rush of a textbook definition, but with the slow, steady pace of a conversation where each layer is laid gently on top of the last, until by the end, the word galaxy feels clear, grounded, and less like a distant abstraction. The first place to begin is with the stars. A galaxy is, at its most visible, a collection of stars bound together by gravity. Hundreds of billions of them in the case of the Milky Way, fewer in the case of dwarf galaxies, more in the case of giants. These stars are not scattered randomly through space, but grouped into patterns, disks, and halos that hold together for billions of years. The glue that keeps them united is gravity, pulling each star toward every other, while their collective momentum keeps the system stable. Without gravity, stars would drift apart, scattered across the universe like sparks in the wind. But because of gravity, they remain bound, circling a common center, orbiting like planets around a sun, only on a far grander scale. But stars alone do not tell the whole story. The galaxy also contains gas and dust, the raw material from which new stars are born. These clouds are often spread thinly across vast regions, invisible to the naked eye, but glowing in radio and infrared light. Within them, under the right conditions, gravity can pull matter together, compressing it until nuclear fusion ignites and a new star shines. Galaxies, then, are not just collections of stars. They are factories where stars are continually created and destroyed, where the cycle of birth and death plays out across eons. A single galaxy can contain regions where stars are being born in clusters, glowing blue and hot, alongside regions where ancient stars are fading into dim red embers. It is a system that holds both youth and age, vigor and decline all at once. There is another ingredient that makes galaxies what they are, one that is less visible but no less important. That ingredient is dark matter. When astronomers measure how galaxies rotate, they find something puzzling. The stars at the outer edges are moving faster than expected, as though held in place by an invisible hand. The only way to explain this is to propose that galaxies contain far more mass than what we can see. This unseen mass does not emit or absorb light, but it exerts gravity, shaping the motion of stars and gas. By every estimate, most of a galaxy's mass is dark matter. Without it, galaxies as we know them could not exist. So when we say galaxy, we're talking about a structure made of stars, gas, dust, and also a vast, invisible halo of matter
that outweighs everything we can see. Galaxies also contain central features, often supermassive black holes. These monsters, millions or billions of times the mass of the Sun, sit quietly at the cause of galaxies, their gravity influencing the orbits of stars nearby. Some are active, feeding on gas and dust, releasing jets of energy that shine across the universe. Others, like the one at the center of the Milky Way, are comparatively quiet, only occasionally flaring when a stray star or cloud wanders too close. The presence of these black holes suggests that galaxies and black holes grow together, each shaping the other over cosmic time. To define a galaxy without mentioning its core would be to leave out the heart of the system.
So far, we have listed the pieces: stars, gas, dust, dark matter, and black holes. But a galaxy is more than just the sum of its parts. It is also about structure. Galaxies come in shapes that astronomers classify: spirals with elegant arms, ellipticals that appear smoother and more rounded, irregulars with no defined shape. The Milky Way is a barred spiral, meaning that at its center there is a bar-shaped concentration of stars from which the spiral arms extend outward. These categories help us describe galaxies, but in reality, each one is unique, shaped by its own history of growth and collisions. Galaxies merge with each other, collide, and sometimes tear one another apart, only to settle into entirely new forms. They are not fixed islands. They are evolving systems, shaped by both their internal motion and the larger environment of the universe around them. To better understand what a galaxy is, it helps to think about what it isn't. A galaxy is not simply a loose grouping of stars drifting through the same region. It is not a temporary arrangement of celestial objects that just happen to be nearby. It is a gravitationally bound system, a family of stars and matter held together strongly enough to endure for billions of years. It is not just a visual pattern like a constellation seen from Earth. Those shapes are illusions, stars that seem close together but are actually separated by vast distances. A galaxy, by contrast, is a real physical structure, an island in the universe that holds itself together. Another way to define a galaxy is through its scale. At the smaller end are dwarf galaxies, containing as few as a few 100 million stars. These are still immense by human standards, but tiny compared to giants. At the large end are galaxies with trillions of stars, stretching hundreds of thousands of light years across. In between are galaxies like our own, mid-sized spirals with a few 100 billion stars. Each type has its role. Dwarfs are often satellites of larger galaxies, orbiting them and sometimes merging into them. Giants dominate clusters, their gravity pulling in smaller companions. The range of size is vast, but the definition holds. A galaxy is a system large enough and cohesive enough to be self-sustaining over billions of years. The question of what exactly a galaxy is has not always been clear. A century ago, astronomers debated whether the spiral shapes seen through telescopes were nebulae inside the Milky Way or separate island universes beyond it. The answer came in the 1920s, when Edwin Hubble measured the distances to these spirals and showed that they were far outside our galaxy, entire systems of their own. That realization expanded the scale of the universe dramatically. Suddenly, the Milky Way was no longer the universe, but just one among many galaxies. Since then, our understanding has only grown. With space telescopes, we now see billions of galaxies, each one a system in its own right. The word galaxy has become a basic unit of cosmic structure, as fundamental as the word star or planet, but on the grandest scale. When you hold that word in mind now, let it feel less like jargon and more like a description of place. A galaxy is a home for stars, a cradle for new light, a container of history stretching back almost to the beginning of the universe. It is a balance of gravity and motion, a visible and invisible matter of order and chaos. It is not simply something to look at through a telescope, but the actual environment in which every star we know resides. Even the universe itself, when described on large scales, is a collection of galaxies. In that sense, galaxies are the bricks of the cosmic wall, the units from which the universe is built. Think again about the Milky Way, not now as a unique object, but as one example of this definition. It is a barred spiral with hundreds of billions of stars, surrounded by a dark matter halo containing gas, dust, and a supermassive black hole at its core. That description is enough to classify it as a galaxy. But then imagine Andromeda, our nearest large neighbor. It is another spiral, larger than the Milky Way, with its own black hole, its own arms, its own billions of stars. And imagine dwarf galaxies like the Melanic Clouds, smaller companions orbiting us. All of them are galaxies too, because they fit the same pattern: bound systems of stars and matter stable over cosmic time. If you were to look outward from our galaxy, you would see others scattered through space, sometimes alone, sometimes in groups. These groupings form clusters, which then form larger structures. But at the core of it all, the basic unit remains the galaxy. In this sense, to ask what a galaxy is to ask what the fundamental building block of the visible universe is.
Without galaxies, there would still be stars, but they would not be organized into enduring systems. Without galaxies, the night sky would not show shapes and bands, but only random sparks. With galaxies, the universe takes on structure, patterns that can be mapped, measured, and understood. Now, let your thoughts drift back to that simple word, galaxy. It is easy to let it roll off the tongue without thinking, but inside, it is a richness that deserves time to unfold. It is a word that means home for billions of suns. It means cycles of creation and destruction. It means hidden halos of dark matter, unseen but essential. It means histories of collisions and merges, scars written in the orbits of stars. It means diversity of form from spirals to ellipticals to irregulars. And it means scale stretching across tens to hundreds of thousands of light years. To define it is not to shrink it, but to appreciate how much the word carries.
In the quiet of this evening, with the stars still imagined overhead, you can let that definition settle. A galaxy is not something far away. It is the structure we live inside. To know what it is to know where we are. And once that foundation is in place, once the meaning of the word feels less like a mystery and more like a description, we can move outward again. When you think of the Milky Way, it is tempting to imagine the hazy band that stretches across the night sky, the faint milky glow that gave the galaxy its name. That view is beautiful, but it is also deceptive, because from our place within the disk, we cannot see the true outline of our galaxy. It is like trying to understand the shape of a forest while standing in the middle of it. The trees around you give a sense of density, but only from above could you see the full pattern of the woods. For centuries, astronomers had the same problem with the Milky Way. They could see the stars spread out in a broad plain, but only in the last century,
have we begun to understand the full shape and size of our galactic home. Tonight, we will let that picture unfold carefully so that the galaxy becomes less like a vague, glowing band and more like a map we can hold in our minds. The Milky Way is what astronomers call a barred spiral galaxy. This means it is shaped like a disk, with long spiral arms curling outward from a central bar of stars. If you could rise above it, you would see a bright core, a thin, elongated structure of stars, and then sweeping arms that extend around it like ribbons. The whole disk is flat, about 100,000 light-year across and only about 1,000 light-year thick. In human terms, that thickness is almost nothing compared to the width, like a thin sheet of paper stretched to a size larger than we can imagine. This thinness is why the galaxy appears as a narrow band in our sky. From inside, looking across the disk, we see layer upon layer of stars packed together.
While looking perpendicular to the disk, we see fewer stars and more empty space. At the very center of the Milky Way is the bulge, a rounded structure containing older stars, dense clouds of gas, and the supermassive black hole known as Sagittarius AA. The bulge is not perfectly spherical, but slightly elongated, giving the appearance of a bar when viewed from certain angles. This bar is a defining feature of the Milky Way structure, extending for about 27,000 light-years across the core. From the ends of this bar, spiral arms emerge, winding outward with a graceful curve. These arms are not solid objects, but regions of higher density where gas and stars are more concentrated. As stars orbit the galaxy, they move in and out of these arms, creating the impression of continuous structures, even though the stars themselves are always changing. Astronomers have identified several main spiral arms in the Milky Way, though mapping them precisely is challenging because of our position inside the disk. The major arms include the Perseus arm, the Scutum Centaurus arm, and the Sagittarius arm. Our solar system lies in a smaller branch known as the Orion arm, or Orion spur, between the Sagittarius and Perseus arms. This location is roughly halfway from the center to the outer edge of the disk, about 27,000 light-years from the galactic core. It is a relatively quiet neighborhood, not too crowded with stars, not too close to dangerous regions near the center, and not so far out that the density of matter is too low. In cosmic terms, it is a stable and fortunate address. The disk itself is not smooth, but layered with features. There is a thin disk containing most of the stars and gas, and a thicker disk containing older stars with slightly different orbits. Surrounding both is the halo, a roughly spherical distribution of stars and dark matter that extends far beyond the visible disk. This halo contains ancient globular clusters, each a dense ball of hundreds of thousands of stars orbiting the galaxy like satellites. The halo also contains most of the galaxy's dark matter, invisible but essential for holding the structure together. Without this hidden mass, the outer stars would drift away. Instead, they remain bound, orbiting faster than they otherwise should. Proof that unseen matter outweighs the visible stars. The scale of all this is difficult to picture. A single light year is about 10 trillion kilometers. To cross the disk of the Milky Way at the speed of light would take 100,000 years. At the speed of our fastest spacecraft, it would take billions. This means that from one side of the galaxy to the other, stars are separated by distances so large that even imagining travel between them is daunting. Yet, within this disk are hundreds of billions of stars, most of them with planets spread across the spiral arms, like grains of sand on a beach. If you could look at the Milky Way from above, you would see these stars glowing in a faint disk, brighter toward the center, thinner toward the edges,
threaded by dark lanes of dust that absorb light. The galaxy would look majestic, but also delicate, a luminous pinwheel suspended in darkness. The size of the Milky Way is not just a number, it is also a timekeeper. Our solar system orbits the center of the galaxy once every 230 million years. That means in the entire history of Earth, about 4.5 billion years, our planet has circled the galaxy roughly 20 times. Dinosaurs saw a completely different part of the galaxy than we do now. The continents drifted, life evolved, and the solar system moved quietly along its orbit, carrying us with it through the spiral arms. Each lap is so long that entire species rise and fall in the time it takes to complete one circuit. The size of the Milky Way is measured not just in distance, but in the ages it takes to move through it.
The galaxy is also not static. Its shape and size have been influenced by interactions with other galaxies. The Milky Way is currently absorbing smaller dwarf galaxies, their stars stretched into streams that weave through the halo. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy, its nearest large neighbor. That collision will reshape both galaxies, merging them into a new, larger elliptical galaxy over billions of years. For now, though, the Milky Way's form remains that of a barred spiral, stable enough that we can describe it with confidence, yet dynamic enough that change will inevitably come in the distant future. One of the difficulties in describing the Milky Way's shape is that we can't step outside it. Instead, astronomers rely on indirect approaches. By charting the positions and motions of stars, by observing how gas is distributed using radio telescopes, and by studying how dust absorbs light, they piece together an image of the disk. The Gaia spacecraft has played a crucial role, measuring the positions and velocities of over 1 billion stars with extraordinary precision. With that information, scientists can trace the spiral arms, determine the thickness of the disk, and even identify ripples left behind by past interactions. The result is a map that, while still not complete, offers the clearest picture we've had of our galaxy's true structure. The values used to describe the Milky Way's size are precise, but also somewhat flexible, because a galaxy doesn't have a sharply defined edge. Unlike a planet with a clear boundary, a galaxy gradually fades into the darkness of space.
The stars grow more sparse, the gas becomes thinner, until eventually the line between the galaxy and intergalactic space becomes difficult to define. Estimates of the Milky Way's size vary depending on whether you measure just the bright disk, about 100,000 light-years across, or include the dark matter halo, which may extend to 300,000 light-years or more. In that sense, the Milky Way is larger than its visible stars suggest, its true size hidden in an invisible envelope. Thinking about this shape and size can feel overwhelming, but there is comfort in letting the details settle slowly. The Milky Way is not just an abstract object. It is the home that holds our Sun, our Earth, and our history. Its spiral arms are the pathways along which stars are born. Its halo is the protective shell that holds it together. Its central bar and bulge are the anchor around which everything orbits. To know its shape is to know the architecture of our home. To know its size is to understand the scale of the stage on which all of human history and all of life on Earth has unfolded. Imagine once more that you're standing under the night sky, looking up at the hazy band of the Milky Way. Now, instead of seeing only a ribbon of light, imagine the full disk stretched out above you, 100,000 light-years wide, arms curling outward, stars scattered by the hundreds of billions. Imagine that your own sun is just one tiny point circling slowly in the Orion Arm. Imagine that around you, unseen, is a halo of stars and dark matter extending 3 times farther than the disk itself. The night sky becomes not just a collection of lights, but the inside view of a vast spiral system. A home so large that it takes hundreds of millions of years to complete a single orbit. As you let that picture form, notice how the Milky Way becomes less abstract. It is not only a name or a glowing band, it is a structure with shape, size, and features that can be described. It is thin, flat, and wide, with arms that curl from a central bar. It is hundreds of thousands of light years across if you include the halo. It contains not just stars, but the unseen mass of dark matter. It is not static, but evolving, shaped by time, motion, and gravity. All of these details build a map, and though we may never step outside the galaxy to see it directly, our minds can hold that map, turning it gently until it feels familiar. Let's stay with the picture of home a little longer. A barred spiral 100,000 light years across, with arms, bulge, halo, and black hole containing hundreds of billions of stars. This is where we live. This is the shape and size of our galaxy. Now that we have settled into the shape and size of the Milky Way, it feels natural to lift our gaze a little further outward, as though we were stepping off the porch of our home to look at the neighborhood around us.
A galaxy on its own is already immense, but it does not float through space in total isolation. It belongs to a community of galaxies, groups bound together by gravity, drifting and circling in patterns that play out over billions of years. When we begin to picture that neighborhood, the Milky Way becomes one member of a family, and the scale of our surroundings grows again. Tonight, let's take a slow walk through that cosmic neighborhood, placing the Milky Way in its local group, and then following the threads that connect galaxies into even larger structures. The most immediate neighbor to the Milky Way is the Andromeda Galaxy. This is the nearest large spiral, larger than our own, about 2 million light years away. That distance is staggering by human standards, but in cosmic terms, it makes Andromeda practically next door. If our galaxy is a house, Andromeda is the neighbor across a wide field, visible through the trees, but still close enough to notice. In fact, Andromeda is visible to the naked eye from Earth on clear, dark nights, appearing as a faint smudge in the sky. Through telescopes, it reveals itself as another barred spiral filled with hundreds of billions of stars with arms and dust lanes, much like the Milky Way. Knowing that such a vast system hangs quietly in our sky is one of the most grounding realizations astronomy can offer. The smudge you see is not just a patch of light. It is an entire galaxy, comparable in size and structure to our own, waiting across the void. Alongside Andromeda and the Milky Way are smaller companions. These are dwarf galaxies, less massive but still important parts of the neighborhood. The large and small melanic clouds are 2 of the most famous. Visible from the southern hemisphere as irregular patches of light, these dwarfs orbit the Milky Way, their stars and gas slowly being drawn in by our galaxy's gravity. Streams of material extend from them, evidence of the tug-of-war between small and large systems. The Milky Way has dozens of such companions, faint dwarfs that circle like satellites. Many of them discovered only recently as astronomers developed better surveys. Andromeda has its own collection of dwarfs too, creating a pair of galactic families facing one another across the intergalactic gap. Together, the Milky Way, Andromeda, and their satellites form a local group. This is the official name for our cosmic neighborhood, a collection of more than 50 galaxies bound together by gravity.
Most of them are dwarfs, faint and irregular, but the Milky Way and Andromeda dominate. Between them lies a balance of pull, a gravitational dance that will one day bring the two giants together. In about 4 billion years, the Milky Way and Andromeda will collide, merging into a single, larger galaxy. For now, though, they drift toward one another, closing the gap at about 100 kilometers per second, a speed that sounds fast, but will still take billions of years to complete. That slow inevitability is part of what makes the local group a true neighborhood. Its members are bound, not free to escape, moving together through space in patterns that can only be measured on cosmic timescales. The local group itself is not large by universal standards. It spans about 10 million light-years across, which is only a fraction of the observable universe. Within that volume, the galaxies are scattered, separated by millions of light-years of empty space. If you could step outside and look back, the local group would appear as a loose cluster, with 2 bright spirals in the middle and a scattering of faint companions around them. It is not crowded like a city, but sparse like a rural landscape, with long stretches of darkness between glowing islands. This disparity is part of the nature of galaxies. Even when they gather, the spaces between them remain vast, reminding us that emptiness is as much a part of the universe as light. Beyond the local group lies another layer of the neighborhood. The local group itself belongs to a larger structure known as the local sheet, a flattened arrangement of galaxies that includes several nearby groups. You can think of the local group as a single household, and the local sheet as the street where we live. Other groups, like the M81 group and the Centaurus group, line this street, each with their own bright galaxies and faint companions. Together, they form a pattern that isn't random, but shaped by gravity, cosmic expansion, and the distribution of dark matter. The local sheet spans roughly 30 million light-years, and within it, galaxies drift slowly relative to one another, creating a sense of stability across billions of years. One of the most significant structures near us is the Virgo cluster. This cluster is located about 65 million light-years away and contains over 1,000 galaxies. It serves as the central hub of a much larger structure called the Virgo supercluster, of which our local group is just a small part. The Virgo cluster is like a city compared to our quiet town, filled with galaxies packed closely together, interacting, colliding, and shaping one another. Some of the galaxies in Virgo are giant ellipticals, containing trillions of stars. Others are spirals like ours, caught within the cluster's gravitational web. The cluster itself is held together not only by the visible galaxies, but by an even greater amount of dark matter, a reminder that what we can see is only part of the full picture. As astronomers mapped these clusters and groups, they began to see patterns on even larger scales. Galaxies not scattered randomly through the universe, they're arranged in filaments and walls, vast chains stretching across hundreds of millions of light-years. Between them lie voids, enormous regions almost empty of galaxies. The result is a structure known as the cosmic web, a pattern of light and darkness that resembles a sponge or a network of veins. Our local group lies on one of these filaments, connected to larger structures that extend beyond what we can easily picture. In this web, galaxies are the bright nodes, groups are the intersections, and clusters are the hubs, all connected by invisible strands of dark matter and gas. This tour of our cosmic neighborhood is more than a list of names and distances. It is a way of placing ourselves within the hierarchy of the universe. At the smallest scale, we belong to the solar system orbiting our star. At the next scale, we are part of the Milky Way,
orbiting the galactic center. At the next, we are members of the local group, bound with Andromeda and dozens of dwarfs.
Beyond that, we are part of the Virgo supercluster, which itself is just one piece of the larger Alenia supercluster, a vast structure encompassing 100,000 galaxies. Each layer is both grounding and humbling, reminding us that our home is part of a system that grows larger and larger with every step outward. The word neighborhood can sometimes make the cosmos sound smaller than it is. But in truth, it is a useful way of thinking. Just as in the human neighborhood, some houses are close together, while others are farther apart. Some are small, some are large, some are tidy, some are crowded. And like neighborhoods on Earth, these galactic communities are not isolated. They interact, influence one another, and evolve together. Our cosmic neighborhood is defined not only by what galaxies are nearby, but by the ways in which their gravity links them, pulling them into patterns that will play out long after our species is gone.
Standing under the night sky, you can remind yourself that everything you see is inside one galaxy, the Milky Way. But beyond that faint band are neighbors invisible to your eyes, too far and faint to appear without telescopes. The Andromeda Galaxy, the Melanic Clouds, the faint dwarves of the local group. They're all out there, silent companions in the dark. And beyond them, clusters and superclusters, filaments and voids, stretching into patterns so large that the mind can only begin to grasp them. Yet, in all of this, the word neighborhood still feels right. Because whether we are speaking of the house next door or the galaxy next door, the sense of belonging remains. We are not alone. We live in a community, one that is vast and ancient, but still a community all the same. As we finish this slow walk through our surroundings, the scale of the neighborhood becomes clearer. The Milky Way is our home. Andromeda is the great neighbor across the way.
Dozens of dwarfs are like smaller houses clustered nearby. Together they form the local group, which itself lies on the edge of larger clusters and filaments. Part of a supercluster, part of a web. Each step outward adds distance, but it also adds connection. A galaxy is not an island. It is one node in a vast network. And as we continue outward, we will see that this network extends not just across our local patch, but across the entire observable universe. A neighborhood so large that it becomes the universe itself. When we talk about galaxies, the numbers quickly become overwhelming. Hundreds of billions of stars, trillions in the larger systems, and more still when we zoom out to the universe itself. But to make sense of such scales, it helps to slow down and focus on one question at a time. Rather than trying to picture all the galaxies scattered across the universe, let's pause here in our own backyard and think carefully about the stars that fill just our galaxy.
Counting the stars of the Milky Way is not something that can be done with a tally sheet and a telescope. It is a task that blends measurement, estimation, and imagination. And while the exact number remains uncertain, the process of arriving at it is as fascinating as the number itself. Tonight, let's count the stars, not by naming them one by one, but by following the methods that allow astronomers to take something so vast and turn it into something we can describe. The first thing to acknowledge is that no one has ever counted every star in the Milky Way. Even if we could, many of them are too faint to see with any telescope we currently have.
Stars like our Sun are bright enough to be visible across great distances, but red dwarfs, which make up the majority of stars, shine so dimly that they blend into the background. In addition, clouds of dust obscure large regions of the galaxy, blocking visible light and making the count even more difficult.
So, when we talk about counting stars, what we really mean is estimating their number based on models of how stars are distributed and how galaxies behave. It is a little like trying to estimate the number of trees in a forest by standing in one part of it, counting what you see, and then applying that average to the entire area. You cannot see every tree, but you can still come to a reasonable figure. Astronomers approach this problem in several ways. One method is to measure the mass of the Milky Way. By estimating how much mass the galaxy contains and then dividing by the average mass of a star, they can arrive at an approximate number of stars. Of course, not all of the galaxy's mass is in stars. Some of it is in gas, dust, planets, and the dark matter that outweighs everything else. But by subtracting what is not starlight, scientists can get closer to the true figure. This approach suggests that the Milky Way contains between 200 and 400 billion stars.
That is a range, not a precise number, but it is accurate enough to give us a sense of the scale. 200 billion is already beyond comprehension. 400 billion doubles it, making the galaxy feel even more crowded. Somewhere within that range lies the truth. Another method is to count stars in specific regions and then extrapolate. By carefully surveying small patches of the sky, astronomers can measure the number and type of stars in that area, then use that information to model the larger disk. This method requires understanding how stars are distributed by type and age. Younger stars are often found in the spiral arms, while older stars are more common in the bulge and halo. Red dwarfs dominate in number, but contribute less light. Giants and supergiants are rare but extremely bright. By combining these factors, scientists can create what is called the initial mass function, a kind of formula that describes how many stars of each type should exist.
Applying that formula across the galaxy makes it possible to estimate the total population, even if we can't observe every single star. To make this easier to picture, imagine standing inside a crowded stadium at night. From your position, you can clearly see the people closest to you. With binoculars, you can see farther into the crowd, but even with the best possible view, you still can't count everyone in the stands. So, instead, you might count one section, then assume the rest of the stadium is filled in a similar way. That estimate won't be exact, but it will be close enough to describe the overall crowd. Counting stars in the galaxy works in a very similar way, except the stadium is 100,000 light-years across, and the audience is made up of hundreds of billions of glowing suns. One of the surprising results of this method is realizing how many stars are simply too faint to notice. The brightest stars in the night sky, the ones we can name, represent only a tiny fraction of the total. Most stars in the Milky Way are dim red dwarfs, smaller and cooler than the Sun, shining so faintly that they can't be seen without telescopes. These red dwarfs make up perhaps 3/4 of all stars. Imagine if you could suddenly turn off the brighter stars and see only the red dwarfs. The night sky would still be full, but with a softer, subtler light. Then imagine the opposite. If the red dwarfs disappeared, the sky would look almost empty. The galaxy is crowded, but its crowdedness is hidden in the dimmest lights. Another layer of complexity comes from the fact that stars are not evenly spaced.
Some regions of the Milky Way are dense with stars, such as the central bulge, where they are packed tightly together. Other regions, like the outer disk, are much more sparse. There are star clusters, both open clusters containing younger stars and globular clusters containing ancient ones.
There are stellar nurseries, where clouds of gas are forming new stars, and stellar graveyards where supernovae have left behind remnants. Counting stars means not only adding them up, but also understanding how they arranged like a city with neighborhoods that vary in density. Some streets are crowded with houses. Others stretch with space between them. The galaxy has the same variety. One might ask, why does it matter how many stars there are? On one level, the number itself is not as important as the process of arriving at it. But knowing the number of stars helps astronomers understand the mass of the galaxy, its evolution, and the likelihood of planets and life. If the Milky Way contains 400 billion stars, and if even a small fraction of them have planets in habitable zones, the potential number of Earth-like worlds is immense. Even if most are lifeless, the possibility of life elsewhere grows with every star added to the count.
In this way, counting stars is not just a numerical exercise. It is a way of estimating our chances of having company in the cosmos. It is also a way of appreciating our place. Out of hundreds of billions of stars, we orbit one. To think that our sun is just one among so many can make it seem ordinary, and yet to us, it is extraordinary. The star that gives us light and life. In this sense, counting stars is humbling, but it is also reassuring. The galaxy is full of suns, but this one is ours. It anchors us in the middle of an ocean of light. The tools astronomers use to count stars are themselves remarkable. Surveys like the Sloan Digital Sky Survey and the Gaia mission provide detailed maps of stars across the sky. Gaia, in particular, has measured the positions and motions of more than 1 billion stars, creating a three-dimensional map of the Milky Way. With that data, scientists can refine their estimates, narrowing the range of possible totals. Yet, even with such precision, uncertainties remain. Dust clouds hide stars from view. Distances are hard to measure at the far edge of the disk. The galaxy is too vast for any survey to be complete. So the number, 200 to 400 billion, remains the best we can say. A reminder that even with the most advanced instruments, the universe retains its mysteries. Think again of standing under the night sky. From Earth, without a telescope, you can see only about 6,000 stars, in total spread across the whole sky. That is the naked eye view. With binoculars or a small telescope, you can see thousands more. With larger telescopes, millions. But even then, you're seeing only the tiniest slice of the true total. Imagine a jar filled with marbles, so many that you cannot possibly count them all. You scoop out a handful, count those, and then multiply by the number of handfuls that would fill the jar. That is how the number of stars in the Milky Way is found. It is not a direct count, but an informed estimate, grounded in observation and guided by theory. There is a certain beauty in the fact that we cannot know the exact number. The galaxy is too vast, too complex, too filled with hidden light for us to catalogue completely. And yet we can still describe it, still place boundaries around it, still say with confidence that hundreds of billions of stars share this spiral with us. That balance between not knowing precisely and still knowing enough is part of the wonder of astronomy.
It reminds us that the cosmos is not a puzzle to be solved completely, but a landscape to be explored, one estimate at a time. If our galaxy alone contains that many, then what happens when we place it among billions of galaxies in the universe? The numbers multiply until they reach heights we cannot comprehend. But before we make that leap, it is worth lingering here in our own backyard with the stars that surround us. Each one is a sun. Each one has its own story, and together they form the luminous body of the Milky Way. Counting them may be impossible in practice, but understanding their abundance gives us a deeper sense of where we live. We're not adrift in emptiness. We're embedded in a sea of light, a sea so wide that even the word billions feels small. When we picture the Milky Way, we tend to imagine something with edges, the way a map of a country has borders drawn around it. Our minds like clear boundaries because they make the world easier to describe. But galaxies are not like countries or cities. They do not have sharp outlines or fences marking where they stop and empty space begins. Instead, they fade gradually, their stars thinning out, their gas becoming more sparse, until eventually the distinction between galaxy and the wider universe is blurred. So, the question of where the galaxy ends is not straightforward. It is one of those questions that seems simple on the surface, but becomes more subtle the longer you sit with it. Tonight, let's take our time to explore how astronomers try to answer it, what it means for the Milky Way to have an edge, and what lies beyond that edge in the spaces between galaxies. The most obvious starting point is the disk. The Milky Way is a barred spiral about 100,000 light-years across in its main disk. That disk is where most of the stars and gas reside, concentrated in a flat plane with spiral arms curling outward from the center. If you define the galaxy only by the disk, you could say it ends at the point where the stars become too sparse to form a continuous structure. But even that is not a clean line. Stars extend beyond the bright disk, thinning gradually but still present. Dust and gas trail off into the darkness. So while one might say the disk is 100,000 light-years wide, that is more of a convention than a hard boundary.
The edge of the disk is more like the shoreline of a beach at low tide. Always shifting, always uncertain. Beyond the disk lies the halo. This halo is a roughly spherical region surrounding the galaxy, containing scattered stars, globular clusters, and vast amounts of dark matter. Unlike the disk, the halo does not have a clear edge at all. Its stars become fewer and fainter with distance, but they do not suddenly stop. Some stars in the halo orbit hundreds of thousands of light-years from the galactic center. Globular clusters, those dense knots of ancient stars, are found far outside the disk. And the dark matter halo extends even farther, perhaps 2 or 3 times the radius of the visible galaxy. If you include the halo, the Milky Way may be 600,000 light-years across, or more. That is 6 times larger than the disk alone, though most of it is invisible. So where in that picture would you say the galaxy ends? At the edge of the disk? At the faintest halo stars? At the limit of the dark matter envelope? Each definition gives a different answer. Astronomers sometimes use the term viral radius to define the effective edge of a galaxy. This is the distance within which the galaxy's gravity dominates and keeps stars bound. Beyond this radius, the pull of neighboring galaxies and the general expansion of the universe becomes stronger, and objects are no longer part of the system. For the Milky Way, this viral radius is thought to be about 250,000 light-years. Inside that boundary, stars, gas, and clusters are considered members of the galaxy. Beyond it, they belong to intergalactic space or to the gravitational reach of another system. Even this definition is not absolute, because galaxies can overlap and their halos can blend. But it is one way of giving the galaxy a size that makes sense in terms of gravity. Another way to think about the galaxy's end is in terms of motion. Stars in the disk orbit the center in well-defined paths. Stars in the halo also orbit, but more loosely on elongated tracks that can take them far from the core. At some point, a star's orbit can become so stretched that it escapes entirely, pulled away by the gravity of another galaxy or by the general expansion of space. When that happens, the star is no longer bound. It becomes a rogue, wandering the intergalactic medium. In this sense, the edge of the galaxy is defined by the limit of binding. Everything inside is gravitationally tethered to the Milky Way. Everything beyond is free. The Milky Way is not alone in this picture. Our galaxy and Andromeda, along with their satellites, are bound together in the local group. Their halos may even overlap, creating a region where it is difficult to say which galaxy an object belongs to. In this way, the edges of galaxies are not only blurred, but shared. Just as towns in a region can bleed into one another without clear separation, galaxies in a group can overlap, their outskirts mingling. When the Milky Way and Andromeda collide in 4 billion years, their edges will blend completely, and eventually the two galaxies will merge into one. At that point, any definition of where the Milky Way ends will have to change, because the galaxy itself will no longer exist as it does now. The lack of a clear edge can feel unsatisfying. But it is also part of the beauty of galaxies. They're not static objects carved from stone with fixed dimensions. They are dynamic systems shaped by time, gravity, and interaction. Their stars are born in the disk, drift into the halo, and sometimes escape altogether. Their gas is drawn inward, pushed outward, stripped by collisions, and replenished by the death of stars. Their halos are invisible but immense, blending into those of neighbors. The Milky Way does not end the way a wall ends. It fades like the light of a fire as you walk away. Still present, but weaker until eventually it is indistinguishable from the night. This raises another interesting point. The boundary of the Milky Way is not the same for every observer. From Earth, the galaxy appears as a band of light across the sky. To us, its edge is the point where the stars become too faint to see. With a telescope, the edge extends farther. With radio telescopes, farther still, because gas can be traced where stars are absent. With gravitational measurements, the edge stretches to the limits of the dark matter halo. Each instrument draws a different line, not because the galaxy has changed, but because our way of perceiving it has changed. In this way, the galaxy's end is as much about our tools and perspective as it is about the object itself. It may help to compare this to the Earth's atmosphere. Where does the atmosphere end? At sea level, the air is dense. As you rise, it thins. At some point, planes can no longer fly higher. Still, astronauts feel weightless. Though there are still molecules of air present, scientists define the edge of space at different altitudes depending on the purpose. Some say 100 kilometers, others higher. But in truth, the atmosphere fades gradually, with no sharp boundary. The galaxy is similar. It has regions where stars are dense, regions where they are sparse, and regions where they fade into the background. To ask where it ends is to accept that the answer depends on how you choose to define it. This gradual fading is not just a matter of structure. It also reflects the history of the galaxy. Over billions of years, the Milky Way has grown by accreting smaller galaxies. Their stars pulled into the halo. Streams of stars still trace the paths of past mergers, winding around the galaxy like faint rivers. These streams can extend far beyond the visible disk.
Reminders that the Milky Way is still growing, still in the process of defining itself. In this sense, the galaxy's edge is not fixed, because the galaxy itself is not finished. It is a work in progress, always expanding, always absorbing, always changing. Thinking about where the galaxy ends can also shift how we think about our place within it. If you imagine the galaxy as a neatly bounded disk, then our solar system lies somewhere inside with a clear separation between us and the outside. But if you imagine the galaxy as a fading system with stars and matter stretching outward indefinitely, then the boundary between inside and outside becomes less important. We are not contained within rigid walls. We are part of a continuum that extends into the larger universe. The Milky Way does not stop and then give way to the cosmos. It is the cosmos woven into it, merging with it without a dividing line. This perspective can be soothing.
The desire for sharp boundaries is often a human instinct, a way to simplify the world into categories. But the universe is not built that way. It is built on gradients, continuums, and transitions. The edges of galaxies are soft. The edges of clusters are soft. Even the edge of the observable universe is not a wall, but a horizon beyond which light has not yet reached us. Everywhere we look, the universe resists being boxed in. And that resistance is not frustrating, but freeing. It means the cosmos is larger, more open, more continuous than our categories can contain. As we linger on this thought, the Milky Way becomes less like an object and more like a living system. Its disk spins, its arms curve, its stars orbit. Its halo stretches outward invisibly. Its streams of stars trace the paths of ancient mergers. Its gas clouds birth new suns. Its black hole anchors the center. None of these features have sharp edges. All of them blend into one another, overlapping, interacting, changing. To ask where the galaxy ends is to realize that it never truly does. It only fades, dissolves into the wider universe, as though reminding us that nothing in the cosmos is ever fully separate. The Milky Way is not a closed container. It is a structure with a disk, a halo, and a gravitational reach. It ends where stars no longer orbit, where its gravity no longer binds, where its light no longer shines. But even then, its influence stretches farther, overlapping with neighbors, blending into clusters, connecting to filaments. Its end is not an ending. It is a transition, and in that transition, we see the way the universe itself is built, not as a set of separate objects, but as a web of connected parts, each fading into the next. When we left off, we were thinking about where the Milky Way ends and how its edges are less like walls and more like fading boundaries. That naturally leads to another question, one that feels like the next step outward.
If our galaxy fades into space, what lies between it and the next? What is the gap between galaxies? And what fills those enormous stretches of darkness? On a clear night, looking up at the faint band of the Milky Way or the small smudge of Andromeda, it can seem like the sky is overflowing with stars. But that impression comes from being inside a galaxy surrounded by billions of suns. Once you step outside in your imagination and try to picture the distance between one galaxy and another, the emptiness becomes more apparent. Tonight, let's take a slow walk across those spaces, not rushing, but letting the vastness reveal itself gently. The first thing to understand is just how large the gap really is. Our nearest large neighbor, Andromeda, is about 2.5 million light-years away. That is the closest major galaxy to us. And yet, the number itself already stretches the imagination.
Light, the fastest thing in the universe, takes 2 and 12 million years to make the journey. That means when you look at Andromeda through a telescope, the light reaching your eye left that galaxy long before humans existed as a species. To cross the gap at the speed of our fastest spacecraft would take tens of billions of years, longer than the universe has even existed. Andromeda is close in cosmic terms, but unimaginably far in human ones. Between us and that neighbor is not a sea of other stars, not a clutter of matter, but mostly empty space. Empty, though, does not mean completely void. The space between galaxies is not a perfect nothingness. It contains stray stars flung out during collisions or pulled from their orbits by gravitational tides. These rogue stars drift through intergalactic space, shining alone, too far from any galaxy to be considered part of one. They are rare compared to the billions inside galaxies, but still numerous enough that the intergalactic medium is not completely dark. Alongside them are clouds of gas, mostly hydrogen, thinly spread, but stretching across vast distances. This gas is so diffuse that even in regions with some of the highest densities, it would be emptier than the best vacuum we can create on Earth. Yet, when summed over millions of light years, the gas adds up, filling the gaps with a faint presence. In fact, it is thought that much of the universe's ordinary matter exists in this form, hidden between galaxies rather than within them. There is also radiation, the faint afterglow of the Big Bang known as the cosmic microwave background, permeating every corner of space. No matter where you drift between galaxies, this background hum is present, a relic of the universe's birth. And underlying it all is dark matter, invisible and undetectable except through its gravity. This dark matter forms halos around galaxies and filaments that connect them, stretching through the gaps like invisible scaffolding. So while the space between galaxies appears empty, it is actually threaded with unseen structures filled with thin gas, scattered stars, and radiation that has been traveling since the beginning of time. To get a sense of this emptiness, imagine scaling the Milky Way down to the size of a dinner plate. At that scale, Andromeda would be another dinner plate sitting about 4 meters away. Between them would be nothing but air. The plates themselves would contain hundreds of billions of grains of light, but the space between them would be bare. That is the reality of galaxies. They're islands of stars in a vast cosmic ocean, separated by expanses so wide that the islands look isolated. When astronomers first realized that the Milky Way was just one among many galaxies, this was part of what struck them most forcefully. Not only were there countless galaxies, but the distances between them were enormous, far larger than the galaxies themselves. This scale is why galaxies rarely collide, despite their numbers. Within a galaxy, stars can be packed relatively close compared to interstellar distances, though still separated by light years. But between galaxies, the gaps are so wide that even in clusters, direct collisions are rare. Over billions of years, gravity can pull galaxies together,
and when they merge, stars are flung around like sparks. But the process takes vast amounts of time, and most of the universe's history is spent with galaxies drifting quietly in their spaces, not crashing into one another. The gaps act as buffers, giving each galaxy room to evolve on its own before interactions reshape it. The intergalactic medium, though faint, is not static. It is heated by quasars, active galaxies whose central black holes pour out energy.
It is shaped by supernova, which eject gas and metals into space. It is stirred by the movement of galaxies through it, leaving trails and wakes. In recent years, astronomers have used X-ray and ultraviolet telescopes to study this medium, detecting the faint glow of gas in the spaces between galaxies. These observations confirm that the universe is not a vacuum, but a complex environment, even in its emptiest regions. The gaps are part of the story, not just blank spaces. They hold the material that will one day fuel new galaxies and stars, slowly falling inward under gravity or gathering along filaments. The scale of these gaps grows even larger when we move beyond the local group. Between our small cluster and the Virgo cluster lies about 60 million light-years of space. That is 60 million years of travel at the speed of light. A gulf so large that it dwarfs even the distance to Andromeda. These intercluster voids are some of the most empty regions in the universe, with only a handful of stray galaxies scattered across them. They are like deserts, punctuated occasionally by oases where galaxies cluster together in groups. When astronomers map the large-scale structure of the cosmos, they find that these voids dominate. Most of the universe is not filled with galaxies, but with emptiness. The galaxies lie along filaments and walls surrounding the voids, like foam on the surface of water. The gaps are not the exception, they are the rule. And yet, these gaps are not hostile. They are simply vast. They are the canvas on which galaxies exist, the spaces that make the clusters stand out. Without the emptiness, the light would have no contrast, the structures no shape. In a way, the gaps give the universe its form, just as much as the galaxies themselves do. They provide the silence that makes the music of stars audible.
They provide the background that makes the clusters visible. They remind us that space is not crowded, but spacious. That the universe is not filled to the brim, but spread thinly with islands of light separated by oceans of dark. For us living inside a galaxy, it is hard to truly feel the emptiness of those gaps. Our sky is crowded with stars. Our telescopes reveal countless galaxies. Our instruments detect radiation everywhere. But if you were somehow placed in the middle of intergalactic space, far from any galaxy, the view would be starkly different. The sky would be almost completely dark. Only the faintest smudges of galaxies would be visible, scattered thinly across the void. There would be no Milky Way band, no familiar constellations, no sense of crowding. The silence of that place would be profound, the emptiness almost overwhelming. And yet, even there, the cosmic microwave background would still hum. The intergalactic gas would still be present, and the filaments of dark matter would still stretch invisibly around you. The emptiness would not be absolute. It would be subtle, filled with traces, like whispers left after the voices are gone. This perspective also changes how we think about our own galaxy. The Milky Way may feel like a crowded home, but in the wider context, it is just one island surrounded by emptiness. Its light shines because of the darkness around it. Its presence matters because of the gap that separates it from its neighbors.
Without the gaps, galaxies would blur together and the universe would lose its structure. With them, the universe becomes a pattern of islands and oceans, clusters and voids, light and silence. The gap between galaxies is not a flaw in the design. It is the space that makes the design possible. As we reflect on this, the gap becomes less intimidating.
It is not a threatening emptiness, but a reminder of scale. It tells us that the universe is large enough to hold countless galaxies without crowding them. It tells us that our galaxy has room to move, room to evolve, room to orbit its neighbors without constant collisions. It tells us that the cosmos is not just filled with things, but shaped by the spaces between those things. And, in a way, it tells us something about ourselves too. We often focus on what is present on the stars, the planets, the galaxies. But sometimes, the spaces in between are just as important, defining the context and giving meaning to what exists. So the gap between galaxies, though vast and seemingly empty, is part of the fabric of the universe. It is filled with thin gas, stray stars, radiation, and dark matter. It is structured by filaments and shaped by gravity. It is the stage on which galaxies move, the ocean across which they drift.
And while it may seem like a void, it is actually a quiet presence, subtle but essential. From here, we can continue our journey outward to see how these gaps give way to clusters, how galaxies gather in larger structures, and how the universe itself is arranged. For now, though, the thought is steady and clear. Between galaxies lies not nothing, but a vast space that holds the cosmos together. One silence between two songs. When we were thinking about the gap between galaxies, the picture that emerged was of islands separated by oceans of emptiness. But as soon as you step back far enough to see not just 2 or 3 galaxies, but hundreds or thousands, another pattern reveals itself. The islands are not scattered at random. They gather. They cluster. They form structures larger than themselves. The Milky Way, Andromeda, and their companions belong to the local group. That group, in turn, belongs to larger patterns linked by invisible strands of gravity and dark matter.
These links are what astronomers call clusters and superclusters, the great highways along which galaxies travel. To describe them is to shift the scale once more from millions of light years to hundreds of millions, and to see the cosmic web begin to emerge in its fullness. A cluster of galaxies is exactly what the word suggests. A group of galaxies bound together by gravity, packed more tightly than the sparse arrangement of the local group. In a cluster, dozens, hundreds, or even thousands of galaxies orbit a common center of mass, swimming in a pool of hot gas and dark matter. One of the nearest and most famous is the Virgo cluster, about 65 million light-years away. This cluster contains more than 1,000 galaxies, spirals like the Milky Way, elliptical, with trillions of stars and dwarfs scattered throughout. If you could look at Virgo through a telescope large enough to capture it all, the sight would be breathtaking. Galaxies scattered like jewels, so numerous that the sky would seem crowded even across such distances. Clusters are not just collections of galaxies. They are also reservoirs of hot gas, heated to tens of millions of degrees and glowing in X-rays. This intracluster medium contains more mass than the galaxies themselves. A reminder that what we see in visible light is only part of the story. The galaxies drift through this medium like fish and water, their stars unaffected, but their gas stripped and reshaped by the interaction. Dark matter, too, plays a dominant role, its gravity binding the cluster together and creating a well so deep that galaxies cannot escape. In this sense, a cluster is more like an ecosystem than a collection, with galaxies, gas, and dark matter all interacting in complex ways. Clusters themselves gather into even larger arrangements called superclusters. A supercluster is a region of space where many clusters and groups are connected, spanning hundreds of millions of light years. The Virgo cluster is part of the Virgo supercluster, a sprawling structure that includes our own local group as one of its outer members. For decades, astronomers used the Virgo supercluster as a way of describing our cosmic address. We lived in the Milky Way in the local group on the outskirts of Virgo. But as maps of the universe grew more detailed, it became clear that even Virgo was part of something larger still. In 2014, astronomers proposed a new map of the cosmic landscape, naming the larger structure Lania, which means immense heaven in Hawaiian. Lania encompasses not just the Virgo supercluster, but many neighboring clusters stretching across 500 million light-years and containing about 100,000 galaxies. A local group lies on one of its edges, flowing slowly along gravitational currents toward the central region where the Great Attractor, a dense concentration of galaxies and matter, pulls everything inward. This discovery reframed our place in the cosmos once again. We are not only part of the Milky Way, not only part of the local group, not only members of Virgo, but also citizens of Lania, a supercluster so vast that the word immense feels small beside it. The idea of gravitational flow is important here. Galaxies do not sit still within clusters and superclusters. They move along paths shaped by the distribution of mass, like rivers flowing downhill. These paths form what are sometimes called cosmic highways, the invisible routes along which galaxies drift over billions of years. The highways are carved by gravity, channeled by dark matter and filled with thin gas. They're not roads in the usual sense, but they serve the same function, connecting one region to another, guiding motion, shaping structure. When astronomers map these flows, they see the universe not as a random scattering of points, but as a web of connections, each strand leading to a hub, each hub linked to others. The whole pattern stretching across billions of light years. To get a sense of this scale, imagine reducing the Milky Way to the size of a grain of sand. At that scale, the local group might be the size of a small pebble, Virgo the size of a large stone, and Lania a continent. Now, imagine that continent floating in an ocean alongside countless others. Each one a supercluster, with its own rivers of galaxies flowing inward. The universe on the larger scales looks less like a simple void with scattered islands, and more like a vast network, a cosmic web where filaments connect nodes and voids stretch between them like bubbles. Clusters, superclusters, and highways are the architecture of this web. The scaffolding on which the galaxies are hung, the existence of these patterns was not obvious until relatively recently. In the mid-10th century, astronomers still thought of galaxies as mostly isolated, with clusters as exceptions. It was only through large surveys mapping the redshifts of thousands of galaxies that the larger patterns came into view. The first maps revealed walls and filaments, structures so vast that they challenged assumptions about how matter could be distributed. The Sloan Great Wall, discovered in 2003, stretches over 1 billion light-years. The Hercules Corona Borealis Great Wall, discovered in 2013, is even larger. One of the biggest structures known in the universe. These discoveries showed that clusters and superclusters are not the top of the hierarchy. They are parts of an even greater pattern woven into the cosmic web itself.
And yet, even with these colossal dimensions, the structures are delicate. The filaments are thin, the clusters scattered, the voids immense. Most of the universe is still empty, but the parts that are filled reveal a pattern that repeats across scales. Galaxies gather into groups, groups into clusters, clusters into superclusters, superclusters into filaments, and filaments into walls. It is a hierarchy that extends upward as far as we can see, but it may not extend forever. On the larger scales, beyond a few billion light-year, the universe begins to look smooth, the web fading into uniformity. At that level, the clusters and superclusters are ripples on the surface of something even more vast. For us living inside the Milky Way, these clusters and highways are almost impossible to feel directly. Our night sky shows only the nearest stars. A telescope reveals galaxies, but the patterns connecting them are too large to see with the naked eye.
It takes maps, surveys, and simulations to reveal the cosmic web. Yet once you know it is there, the universe feels different. The stars overhead are not just points of light. They are part of a galaxy. That galaxy is part of a group. That group is part of a cluster. That cluster is part of a supercluster. And all of them are connected by highways of gravity, flowing slowly, inevitably, through time. This knowledge also changes how we think about motion. When you walk down a street, you know where the road leads. When you drive along a highway, you know it connects one city to another. In the same way, galaxies drift along cosmic highways, not aimlessly, but along paths shaped by mass. Our local group is moving toward Virgo. Virgo is moving within Laniakea. Lania itself is connected to neighboring superclusters on timescales of billions of years. These flows shape the future of the universe, guiding collisions, merges, and the formation of new structures.
To see the universe this way is to see it as dynamic, alive with motion. Every galaxy part of a larger current. It is worth pausing to think about what it means to belong to something as large as Laniakea. The word immense heaven feels appropriate because the size is beyond anything we can picture. 500 million light-years across, 100,000 galaxies within it, filaments stretching like rivers, clusters like cities, groups like villages, all connected, all flowing toward the same gravitational centers. And we, on our small planet, orbiting an ordinary star in a spiral arm of the Milky Way, are part of that, not separate from it, not outside it, but within it, moving with it, carried along by the same currents. The scale is vast, but the connection is intimate. The supercluster is not out there, it is here, and we are inside it. It is worth lingering on the image of clusters and superclusters, of cosmic highways stretching across space. These are the structures that shape our neighborhood on the grandest scales. They are the roads on which galaxies travel, the cities where galaxies gather, the continents of the cosmic landscape. They remind us that the universe is not random, but patterned, not chaotic, but structured. And they remind us that even the largest structures we can imagine are still only parts of something larger. When we look at clusters and superclusters, at filaments stretching across hundreds of millions of light years. It is easy to marvel at their scale. But another question soon follows, one that is as practical as it is awe-inspiring. How do astronomers measure something so vast? How do they put numbers to distances so large that light itself takes millions or billions of years to cross them? How can we say that the Milky Way is 100,000 light-years across? That Andromeda is 2 million light-years away? Or that the Virgo cluster spans tens of millions? These are not distances anyone can travel. They are not lengths that can be measured with a ruler or even compared to ordinary experience. And yet, astronomers have found ways to do just that. Tonight, let's walk slowly through those methods, step by step, and see how the immeasurable becomes measurable. The most basic tool is light itself. Every star, every galaxy, every cluster shines, and that light carries information. It spreads outward across space, fading with distance, but never losing the signature of its source. Astronomers use that light as a messenger, decoding its patterns to learn where an object is, how fast it is moving, and even what it is made of. But turning that information into a measure of distance requires creativity. Because there is no direct way to measure how far away something is simply by looking. Instead, astronomers use a set of methods known as the cosmic distance ladder. Each step relying on a different technique, each step building on the last to reach greater and greater scales. The first step of the ladder is parallax. This is the apparent shift in position of a nearby object against a background of distant ones, caused by moving the point of view. You can test it yourself by holding your finger in front of your face and looking at it with one eye, then the other. The finger seems to jump relative to the background. Astronomers use the same principle by observing nearby stars at different times of year when Earth is on opposite sides of its orbit around the Sun. The closer the star, the larger the apparent shift. By measuring this tiny angle, astronomers can calculate the star's distance. Parallax is the most direct and reliable method, but it only works for relatively nearby stars within a few thousand light years, because beyond that, the angles become too small to detect. With instruments like the GEA spacecraft, however, parallax has been measured for over 1 billion stars, creating a precise map of the Milky Way structure. Beyond parallax, astronomers use what are called standard candles. These are objects whose intrinsic brightness is known, allowing their distance to be calculated by comparing it to their apparent brightness. One of the most important standard candles is a type of star known as a Cepheid variable. These stars pulse in brightness with a regular rhythm, and the period of the pulse is directly related to their true luminosity. By measuring the period, astronomers know how bright the star really is. By comparing that to how bright it looks from Earth, they can calculate how far away it must be. Cepheids allow distances to be measured far beyond the reach of parallax into neighboring galaxies. Another standard candle is the type supernova, an explosion of a white dwarf star that always reaches roughly the same peak brightness. Because these events are so luminous, visible across billions of light years, they are essential for measuring distances on the larger scales. By observing their light curves and comparing them to the known standard, astronomers can place galaxies on the cosmic map with remarkable precision. It was the study of these supernovae in the 1990s that revealed the accelerating expansion of the universe, a discovery that led to the concept of dark energy. In that sense, the methods of measurement not only tell us where things are, but also how the universe itself behaves. Spectroscopy provides another tool. When light passes through space, It carries the fingerprint of the atoms that emitted or absorbed it. By spreading light into its spectrum, astronomers can read these fingerprints and learn about the source. But they can also measure something else: redshift. As the universe expands, light from distant galaxies is stretched, shifting toward the red end of the spectrum.
The greater the redshift, the farther the galaxy. This relationship, first discovered by Edwin Hubble, is now one of the most important ways of measuring distance. By calibrating redshift with other methods, astronomers can use it to map galaxies billions of light-years away. It is not perfect. Local motions can add noise, but on large scales, it reveals the structure of the cosmic web. Gravitational lensing provides yet another method. When light from a distant object passes near a massive galaxy or cluster, its path is bent by gravity, creating distortions or multiple images. By analyzing the shape and extent of the lensing, astronomers can infer the mass of the foreground object and the distance of the background one. This technique not only measures distances, but also maps the distribution of dark matter, which reveals itself through its gravitational pull, even though it cannot be seen directly. In this way, measurement becomes a way of uncovering the invisible scaffolding of the universe. Time itself becomes a ruler in some cases. Pulses, the rapidly spinning remnants of massive stars, emit beams of radiation with clock-like regularity. By timing these pulses, astronomers can detect tiny changes caused by motion and distance. Similarly, quasars, bright, active galaxies powered by supermassive black holes, flicker with variability that can be used as a kind of cosmic yardstick. These methods are more experimental, but they show how creative astronomers must be in turning the immeasurable into something that can be described. The cosmic distance ladder is called the ladder for a reason. Each rung supports the next. Parallax calibrate Cepheids, Cepheids calibrate supernovae, supernovae calibrate redshifts, and redshifts extend the reach to billions of light years. Each step builds on the certainty of the one below it, creating a chain of measurement that stretches from the nearest stars to the edge of the observable universe. The process is not flawless. Errors accumulate, and debates continue about the exact values of some distances. But the overall picture is reliable enough to create maps of the cosmos to say with confidence how large the Milky Way is, how far Andromeda lies, and how vast the universe itself must be. It is worth reflecting on how extraordinary this is. From a small planet orbiting an ordinary star, we've found ways to measure the distances to objects so far away that their light has been traveling for billions of years. We've built instruments sensitive enough to detect angles no larger than the width of a human hair seen from across a city. We have found stars whose brightness can serve as yardsticks, explosions whose light can reach across cosmic time, and redshifts that reveal the expansion of space itself. To measure the immeasurable is to stretch imagination and ingenuity to their limits. And yet we have done it, creating a map of the universe that is both humbling and empowering. This knowledge also reshapes how we see ourselves. To know that Andromeda is 2 million light-years away is not just to know a number. It is to know that the faint smudge in the night sky is a galaxy whose light left before humans walked the Earth. To know that the Virgo cluster is 65 million light-years away is to know that its light left when dinosaurs still lived on this planet. To know that the cosmic microwave background comes from 13.5 billion years ago is to know that we are seeing the afterglow of the universe's birth. Measurement turns distant light into a timeline, connecting us to events across cosmic history. The numbers are not just quantities, They are markers of time and place, anchoring us in the story of the cosmos.
At the same time, it is important to remember that every measurement comes with uncertainty. The universe is vast, and our tools, though remarkable, are limited. Distances are refined as instruments improve, as surveys expand, as methods are cross-checked. The numbers shift slightly, the maps become clearer, but the overall picture remains the same. Galaxies are vast, the universe is larger still, and our place within it is both small and extraordinary. The process of measuring is ongoing, a continual effort to sharpen our view of something that will always remain partly beyond reach. As we linger on this thought, the phrase "measuring the immeasurable" becomes less paradoxical. The universe is beyond human scale, but not beyond human curiosity. We cannot step outside and stretch a ruler across galaxies, but we can use light, motion, and gravity as our tools. We can climb the cosmic distance ladder, rung by rung, until we reach the farthest objects we can see. And though there will always be horizons beyond which we cannot measure, the act of trying brings the universe into focus, one step at a time. From the shifting of nearby stars to the redshift of galaxies billions of light years away, we have turned the immeasurable into something describable. And in doing so, we've given ourselves a way to understand scale, to compare the Milky Way to the universe, to see not only how big things are, but also how connected they are. When we think about how astronomers measure the cosmos, what appears is not just a collection of numbers, but a method of stretching the imagination to meet the universe halfway. With parallax, with Cepheids, with supernova and redshifts, we climb step by step along the cosmic distance ladder until we finally reach the widest scale we can observe. That scale is what we call the observable universe. The phrase itself sparks curiosity.
It isn't simply the universe, but the observable universe, implying both a vast expanse and a boundary, a horizon beyond which our instruments cannot see. To approach this horizon is to look as far back in time as the laws of physics allow, to the very edge of light itself. The observable universe is defined by distance in time, not just in space. Light travels at a finite speed. That speed is incredibly fast by everyday standards, nearly 300,000 kilometers per second. But it is not infinite. When you look at the moon, you see it as it was about a second ago. When you look at the sun, you see it as it was 8 minutes ago. When you look at Andromeda, you see it as it was 2 million years ago. Every time you look outward, you are also looking backward. At the farthest limit, the light we observe has been traveling since the universe was very young. That light reaches us as the cosmic microwave background, radiation from when the universe was just 380,000 years old. Beyond that point, there is nothing we can see. The universe was too hot and dense for light to travel freely, so the horizon begins there. To look farther is not possible because there is no light older than that to reach us. This horizon defines the observable universe. It is not a wall, not an edge in the ordinary sense, but a limit created by time. Light has had only 13 times 8 billion years to travel since the Big Bang. But because the universe has been expanding during that time, the distance to the farthest objects we can observe is greater than 13.8 billion light-years. In fact, those objects are now about 46 billion light-years away. That means the diameter of the observable universe is about 93 billion light-years across. This number is almost incomprehensible, so large that even when spoken slowly, it resists settling in the mind. 93 billion light-years. A horizon defined by time and expansion, containing everything we can possibly observe.
What lies within this observable bubble is staggering. Estimates suggest there are about 2 trillion galaxies inside it, each with hundreds of billions of stars. That means the total number of stars is around 10 to 24. A number so large, it is difficult to say aloud without it dissolving into abstraction. That is a 1 followed by 24 zeros. If each star were a grain of sand, they would fill every beach on Earth many times over. And yet, even that number may be conservative, because faint galaxies too dim for current telescopes may number even more. The observable universe is not just vast, it is overflowing with light. To glimpse it is not to see it all at once. Of course, no telescope can take in the whole observable universe. Instead, astronomers build maps piece by piece, surveying patches of sky and stitching them together into a panorama. The Hubble Ultra Deep Field, for example, is one of the most famous glimpses. Pointing the Hubble Space Telescope at a tiny patch of sky, no larger than a grain of sand held at arm's length, astronomers collected light over many days. The result was an image filled with thousands of galaxies, each a swirl or smear of light. Multiply that patch across the sky, and you reach billions. The James Webb Space Telescope has extended this vision even farther, peering into earlier epochs, finding galaxies that existed less than 1 billion years after the Big Bang. These glimpses are like peeking through a keyhole and seeing an entire city beyond, only to realize that the city stretches farther than you can imagine. The observable universe is not uniform, though. It is structured, shaped by the same cosmic web we spoke of before. Galaxies cluster into filaments. Filaments weave into walls, and between them lie vast voids. The largest of these voids span hundreds of millions of light-years, nearly empty, while the densest clusters blaze with galaxies packed tightly together. When astronomers map these structures, they see a pattern that looks almost biological, like neurons in a brain or filaments in tissue. It is a reminder that the universe on its largest scales has a kind of coherence, a pattern that emerges from gravity pulling matter into threads and knots. One of the most humbling aspects of the observable universe is that it is not the whole universe. It is simply the part we can see. Beyond the horizon, the universe almost certainly continues. There is no reason to think that space ends abruptly at 46 billion light-years. It likely extends far beyond, perhaps infinitely, though we cannot observe it. This distinction is subtle but important. The observable universe is not a container, not the whole story, but a bubble defined by the speed of light and the age of the cosmos. To glimpse it is to glimpse a boundary not of the universe itself, but of our vision. This limitation makes the universe feel even more mysterious. We live inside a bubble of light, and everything we know about the cosmos is contained within it. Beyond the bubble, we cannot see, though we can imagine. Perhaps the patterns of galaxies continue. Perhaps they change. Perhaps there are regions so different from ours that they would challenge our understanding of physics. Or perhaps everything looks much the same, repeating endlessly. We cannot know.
The observable universe is as much about what lies beyond our reach as it is about what lies within it. It is striking to think how recent this knowledge is. Barely a century ago, astronomers were still debating whether galaxies outside the Milky Way even existed. The observable universe, as we now describe it, was unimaginable then. And yet, in that short time, we have gone from thinking our galaxy was the whole cosmos to realizing that it is just one among trillions inside a bubble 93 billion light-year across. This expansion of awareness is one of the most profound shifts in human thought, changing not only our scientific models, but our place in the story of existence. To glimpse the observable universe is to glimpse our own smallness, but also our capacity to comprehend. From Earth, the observable universe is centered on us, simply because we see outward in all directions. But every observer anywhere has their own observable universe centered on them. Someone in a galaxy billions of light years away would also see a bubble 93 billion light-year across, but the contents would be different. This fact reinforces that the observable universe is not a physical edge, but a horizon, one that depends on where you stand. It is like standing in the middle of a fog. Each person sees a circle around them, but the fog itself stretches beyond all of them. Our horizon is ours, but it is not the limit of reality. To glimpse this horizon is not only to marvel at its size, but also to feel a kind of quiet comfort. The observable universe contains everything we will ever know. All the galaxies, all the stars, all the light. It is a complete picture, even if it is not the whole story. To live inside it is to live inside a bubble of knowledge, one that expands slowly as time passes, because with each year, light from slightly farther away reaches us. The observable universe is growing, not because space itself is expanding into something, but because more of it becomes visible as light travels. Every second, more of the cosmos enters our sight. More of the past arrives at our doorstep. This thought makes the observable universe not just a limit, but a process. It is a horizon that changes, a boundary that recedes with time. It reminds us that we live not in a static cosmos, but in a dynamic one, where new discoveries are always possible. To glimpse it today is to see one picture. To glimpse it 1,000,000 years from now would be to see more, to add new galaxies to the map, to extend the bubble outward. The observable universe is not fixed. It is a horizon, always in motion, expanding with our view. So when we say we glimpse the observable universe, what we really mean is that we glimpse the farthest light, the faintest signals, the oldest echoes. We see galaxies billions of light years away, their light arriving across time. We see the cosmic microwave background, the afterglow of creation itself. We see structure on the largest scales, filaments and walls spanning hundreds of millions of light years. We see a bubble 93 billion light-year across, filled with 2 trillion galaxies, and beyond it, we imagine more. That is the glimpse. Not everything, but enough to feel the immensity. Enough to know that our galaxy is small compared to the whole. Enough to place ourselves in a cosmos that is larger than words can contain. The observable universe is not the final answer, but it is the farthest view we can take.
To glimpse it is to stand at the edge of knowledge, looking out into a vastness that is both known and unknown, measurable and mysterious, finite in sight, but perhaps infinite in reality. When we take in the picture of the observable universe with its horizon stretching 93 billion light-years across and its contents numbering in the trillions of galaxies, the natural question that follows is how our own Milky Way compares to all of this. We know it is large in its own right, 100,000 light-years across, with hundreds of billions of stars. We know it is a barred spiral with graceful arms and a central bulge anchored by a supermassive black hole. We know it contains dark matter, gas, dust, clusters, and streams. And yet, when placed against the backdrop of the whole observable universe, the Milky Way is not even a giant. It is an ordinary spiral, one among trillions, occupying a fraction of the cosmic expanse. To compare the Milky Way to the universe is to compare a single grain to a desert, a single wave to the ocean. And yet to do so carefully is to give scale to both, to see how our home fits into the whole. The first step is to think about relative size. The Milky Way is about 100,000 light-years across. The observable universe is 93 billion light-years across. To put those numbers together is to place one next to the other. 100,000 compared to 93 billion. That means the observable universe is about 900,000 times larger than the Milky Way in diameter. In volume, the difference is even more staggering. If you cube the ratio, the observable universe is about 10 to the 18th power times larger in volume than the Milky Way. That is a billion times. If the Milky Way were reduced to the size of a coin, the observable universe would be the size of a continent. If the Milky Way were a single drop of water, the observable universe would be an ocean stretching beyond the horizon. The next step is to compare populations. The Milky Way contains between 200 and 400 billion stars. That number is immense on its own, enough that every human alive could have dozens of suns to themselves. But the observable universe contains about 2 trillion galaxies. If each one has an average of 100 billion stars, the total number of stars is around 10 to the 24th power. That is a septillion, a 1 with 24 zeros. Compared to this, the Milky Way stars are a drop in a cosmic bucket, a few 100 billion out of a septillion. To say it another way, if every star in the Milky Way were a grain of rice, it would fill a silo. But if every star in the observable universe were a grain of rice, it would fill Earth's oceans many times over. The numbers multiply until they become overwhelming. And yet, they are precise enough to give us perspective. The Milky Way is also not exceptional in type. It is a barred spiral, mid-sized, with an ordinary supermassive black hole at its center. Galaxies come in many forms. Ellipticals, containing trillions of stars. Dwarf irregulars, with only millions. Spirals, with graceful arms. And lenticulars that are somewhere in between. The Milky Way falls in the middle of this spectrum. Andromeda, our nearest large neighbor, is larger. Ellipticals, like M87s in the Virgo cluster, are much larger still, containing several trillion stars. Dwarfs, like the melanic clouds,
are smaller against the universe. The Milky Way is typical, not the largest, not the smallest, not unusual in shape or features. To us, it feels immense and unique, but in the larger context, it is an average citizen of the cosmos, one spiral among countless others. This ordinariness is, in a way, profound. If the Milky Way were unusual, it might suggest that our place in the universe is special, a rare exception. But the fact that it is typical suggests that the universe is filled with galaxies like ours, each with stars, planets, and perhaps life. It suggests that what we experience here may not be unique, that somewhere in another spiral, there may be suns and worlds not unlike our own. To compare the Milky Way to the universe is not to diminish it, but to see it as part of a larger pattern, a thread woven into a vast tapestry. The beauty lies not in its uniqueness, but in its belonging. To give more tangible comparisons, astronomers often use scale analogies. If the Milky Way were shrunk to the size of a city, the observable universe would be larger than the Earth itself. If the Milky Way were a house, the universe would be a planet. If the Milky Way were a grain of sand, the universe would be a beach stretching for thousands of kilometers. Each analogy helps, but none can fully capture the immensity, because our minds are not built to handle such scales. We can only approximate, gesture, hint at the difference. And yet, even a hint is enough to feel the smallness of our galaxy and the vastness of the universe. The comparison also brings time into focus. The Milky Way is about 13 billion years old, nearly as old as the universe itself. It formed not long after the first galaxies, growing through mergers and accretion. Its stars trace back to nearly the beginning. In this sense, the Milky Way is ancient, but the universe is older still. The first galaxies formed when the universe was only a few 100 million years old. Since then, galaxies have grown, collided, evolved, and changed. The Milky Way is part of that history, a product of cosmic evolution, but not the whole story. To compare the two is to see the Milky Way as a chapter in a much larger book, one of trillions of chapters, each with its own plot, each contributing to the narrative of the universe. Another perspective comes from motion. The Milky Way orbits within the local group, drifting toward Andromeda. The local group itself is moving toward the Virgo cluster. Virgo is moving within Lani Ara. All of these motions are part of the flow of the cosmic web, currents of gravity that shape the universe. Compared to these flows, the Milky Way is a single leaf in a river carried along by forces much larger than itself. The observable universe is like a vast river system spreading across the landscape. This comparison highlights not only a difference in size, but a difference in context. The Milky Way exists within something larger, moving through it, shaped by it, inseparable from it. That realization can feel humbling, but it can also feel reassuring. To understand that our galaxy is ordinary, that it is one among trillions, that it is small compared to the universe, is to understand that we belong to something immense. Our position is not at the center, not at the edge, not unique, but part of a greater whole. The Milky Way is not diminished by the universe. It is completed by it, given context, given meaning. To live in the Milky Way is to live within the universe, not apart from it, not separate, but inside it, woven into it, indistinguishable from it. It's also important to remember that while the Milky Way is small compared to the universe, it is still vast compared to us. 100,000 light-years across, hundreds of billions of stars, billions of planets. To travel across it is impossible on a human timescale. To explore even a small portion of it would take thousands of years. Our lives unfold within a tiny corner of the galaxy. And yet, we can still compare it to the universe. This layering of scale is part of the wonder. We are small compared to the galaxy, and the galaxy is small compared to the universe. And yet, we can comprehend all three. The act of comparison itself is extraordinary, a product of minds that can stretch across billions of light years in thought. Comparing the Milky Way to the universe also raises questions about what lies beyond. The observable universe is only what we can see. Beyond it, the universe may continue indefinitely. In that case, the Milky Way is not one of trillions, but one of an uncountable number scattered across infinite space. Against that backdrop, the difference between 100,000 light years and 93 billion light years becomes almost trivial. Both are small compared to infinity. This possibility does not make the Milky Way less important. It makes it more remarkable that we can know it at all, that we can describe it, that we can compare it to the universe we can see.
As we linger on this thought, the comparison becomes less about numbers and more about perspective. The Milky Way is our home. The universe is the landscape in which that home sits. To compare them is to understand that home is both small and large, both ordinary and extraordinary, both a grain and the galaxy. It is to accept that scale is relative, that meaning does not depend on size, that belonging is as important as immensity. The Milky Way, compared to the universe, is tiny, but for us, it is everything. And in that paradox lies the beauty of the comparison. The Milky Way 100,000 light-year across, with hundreds of billions of stars. The observable universe 93 billion light-year across, with trillions of galaxies. One is our home. The other is the stage. Both are real, both are immense, both are connected. To compare them is to see ourselves in context, to feel the vastness of the cosmos and the intimacy of belonging to it all.
When we compare the Milky Way to the universe as a whole, what stands out most is that galaxies themselves are the fundamental units of structure. The stars, planets, and nebulae that make up our night sky are all contained within a single galaxy. And when we step back, we see trillions of such systems filling the observable universe. Each one is like an island, separated from the others by vast stretches of oceanic darkness. This is why astronomers often speak of galaxies as cosmic islands. The metaphor is simple, but it captures something profound. Galaxies are places of light in an ocean of dark, self-contained worlds where stars are born, live out their lives, and die. They are cradles for planets and nurseries for possibility. To think of them as islands is to picture the universe as an archipelago on the grandest imaginable scale. The image of a cosmic island is not new. In the early 20th century, before it was firmly established that galaxies beyond the Milky Way existed, astronomers debated whether the spiral nebula visible in telescopes were part of our galaxy or separate systems altogether. Some argued they were clouds of gas inside the Milky Way. Others suggested they were island universes, entire galaxies in their own right. It was Edwin Hubble's work in the 1920s that settled the debate, showing that the Andromeda Nebula was far too distant and too large to be part of our galaxy. It was a galaxy of its own. From that moment forward, the universe expanded in our imagination as we came to understand that the Milky Way was just one island among countless others scattered through the cosmic sea. What makes galaxies feel like islands is not only their separation, but their self-contained nature. Each galaxy is bound together by its own gravity, a collection of stars, gas, dust, and dark matter orbiting a common center. Like islands, they're surrounded by vast expanses of emptiness. To travel from one to another is like crossing an ocean. A journey so long that even light takes millions of years. The stars of a galaxy are like the inhabitants of an island, sharing a common home, orbiting within its boundaries. And just as islands can be small or large, lush or barren, so too can galaxies. Some are dwarfs with only a few million stars. Others are giants with trillions. And in between are spirals like the Milky Way, balanced in size and form. The metaphor extends even further when we think about diversity. No two galaxies are exactly alike, just as no two islands are identical. Some are spirals, their arms stretching like graceful coastlines. Some are ellipticals, smooth and rounded, more like ancient worn islands eroded by time. Some are irregulars, jagged and chaotic, shaped by collisions and tides. Each has its own character, its own history, its own story written in the motion of its stars and the glow of its light. To drift across the universe would be to island hop on the grandest scale, moving from one galactic shore to another, each with its own landscape of stars and worlds. Galaxies are also ecosystems, sustaining cycles of birth and death. Within their clouds of gas, stars ignite, shining for billions of years before exhausting their fuel. Some end gently, fading into white dwarfs. Others end violently, exploding as supernova that scatter heavy elements into space. Those elements, carbon, oxygen, iron, and more, seed the next generation of stars and planets. In this way, galaxies recycle themselves, turning old matter into new light, sustaining the cosmic archipelago. Each galaxy is not just an island, but a living island, evolving, changing, reshaping itself over time.
The space between galaxies, the vast ocean of intergalactic voids, makes their island-like nature even more vivid. Inside a galaxy, stars may be separated by light years, but they are still relatively close compared to the emptiness between galaxies. Between the Milky Way and Andromeda, for example, lies 2 and 12 million light-year of space, with only a handful of stray stars. Compared to that gulf, the interior of a galaxy feels crowded. To imagine galaxies as islands is to acknowledge that the spaces between them are real oceans of emptiness, so deep and wide that crossing them is beyond anything we can picture. The islands shine all the brighter because of the ocean that surrounds them. The idea of galaxies as islands also changes how we think about belonging. When you live on an island, you know that your world has boundaries. You can walk to the shore and see the water stretching away in every direction. But you also know that other islands exist far across the waves, even if you cannot see them. To live in a galaxy is much the same. We know the stars around us, the arms of the Milky Way, the structure of our home, and we know that beyond it lie other galaxies, other homes, other islands of light. Even if we will never reach them, their existence shapes our understanding of where we live.
The Milky Way is not the only island. It is one among many, part of an archipelago that stretches across the universe. This perspective can be both humbling and comforting. It is humbling because it reminds us that we're not at the center of everything, not unique, not solitary. Our galaxy is one island among trillions. But it is comforting because it reminds us that we're not adrift alone in the dark. There are other islands, countless others shining across the cosmic sea. We belong to an archipelago, even if the ocean between is too vast to cross.
The stars we see at night are local, but the light of other galaxies reaches us too. Faint smudges that are reminders of neighbors beyond our shores. Galaxies as islands are not static. They move through the ocean, carried by gravity, sometimes colliding with one another. When two galaxies merge, their stars pass by without colliding directly, because the gaps between them are too large. But their shapes are torn, their gas compressed, their structures reshaped. These galactic collisions are like tectonic events in the cosmic archipelago, reshaping islands, creating new forms. The Milky Way itself has grown by absorbing smaller galaxies, and in the future, it will merge with Andromeda to form a larger island. The archipelago is not fixed. It is dynamic, always changing, always reshaping itself. The island metaphor also invites us to think about exploration. On Earth, islands were discovered by explorers crossing oceans, charting coasts, mapping shores. In the universe, we cannot physically sail between galaxies, but we can explore them with light. Telescopes are our ships, photons are winds, and the maps we create are charts of the cosmic archipelago. Each image of a galaxy is a glimpse of another island, another home across the sea. The Hubble Ultra Deep Field, with its thousands of galaxies in a tiny patch of sky, is like standing on a shore and seeing an endless horizon of islands, each waiting to be imagined. This way of seeing galaxies also highlights their role in the universe as containers of possibility. Planets form within galaxies. Life arises on planets, and civilizations, at least ours, emerge under the shelter of a galactic home. If life exists elsewhere, it too will arise within a galaxy on a world orbiting one of billions of stars. Galaxies are not just islands of light, they are islands of potential, each holding the possibility of countless stories.
To think of them as islands is to think of the universe as an archipelago, not only of matter, but of meaning, where each galaxy might hold its own forms of wonder. And yet, there is something more subtle about the metaphor. On Earth, islands are separated by oceans of water, something tangible. In the universe, galaxies are separated by emptiness, something intangible. The ocean here is not a substance to cross, but a void to endure. The distance between galaxies is not just physical, it is temporal. Light itself takes millions or billions of years to make the journey. This makes the islands feel more distant, more unreachable, more isolated. And yet their light reaches us, bridging the gap, reminding us that isolation is not total. The cosmic ocean may be vast, but the islands still shine across it, sending their signals, their presence, their existence. So when we think of galaxies as cosmic islands, we're not just using a poetic image. We are describing something real about the structure of the universe. Galaxies abound, systems of stars and matter separated by enormous gaps, diverse in form, dynamic in motion, and essential to the cosmic web. They are the units of the universe, the homes of stars and planets, the cradles of light and life. They are islands, and the universe is an ocean filled with them, stretching farther than we can see. To live in the Milky Way is to live on one such island, to know one shore among countless others, to belong to an archipelago of unimaginable size. After imagining galaxies as islands scattered across the dark ocean of space, the next question arrives almost automatically. How many of them are there? If the Milky Way is one island, and if the observable universe is an ocean filled with trillions more, can we ever hope to count them all? The question has been asked for as long as astronomers have been able to see beyond the limits of the naked eye. And while we now have estimates that are breathtaking in their scale, the answer is still open-ended, still uncertain, still evolving as our tools improve. To ask how many galaxies are out there is not only to ask about numbers, but also about how we know what we know, how we measure, how we infer, and how we confront the immensity of the universe. The first thing to recognize is that galaxies cannot be counted directly, one by one, across the entire sky. The observable universe is simply too vast, and most galaxies are too faint to see with any telescope we currently have. Instead, astronomers approach the problem by sampling small regions of the sky in great detail, then using those samples to estimate the total. One of the most famous of these samples is the Hubble Deep Field, and later the Hubble Ultra Deep Field.
By pointing the Hubble Space Telescope at a tiny patch of sky
And collecting light over many days, astronomers revealed thousands of galaxies in an area no larger than a grain of sand held at arm's length. Extrapolating from that image across the entire sky suggests billions upon billions of galaxies. The later Hubble Frontier Fields and now the James Webb Space Telescope have extended this work even farther, pushing back to earlier epochs of the universe and revealing galaxies that formed only a few 100 million years after the Big Bang. Based on this kind of sampling, estimates have changed dramatically over the years. For much of the 20th century, astronomers thought there might be a few 100 billion galaxies in the observable universe. But in 2016, a team analyzing deep field data concluded that the true number might be close to 2 trillion. That is 1,000 times larger than the number of galaxies catalogued at the time. Many of these galaxies are small and faint dwarfs that are difficult to detect with current instruments, but they still count as galaxies, self-contained systems of stars and matter orbiting together. The discovery that there may be 2 trillion galaxies reshaped our understanding of just how crowded the cosmic archipelago really is. And yet, even this number may not be finer. As telescopes improve, as surveys grow deeper and wider, we may find that the number is higher still. Many galaxies may lie hidden in the faintest reaches of the universe, too dim or too diffuse for us to detect. Others may have merged or been disrupted over time, leaving behind only remnants. Counting galaxies is like counting trees in a forest while standing in a clearing. You can see the nearest ones clearly, estimate the density and project outward, but there will always be trees hidden behind others. Trees too small to notice, trees beyond the horizon. The forest is larger than any count can fully capture. Another complexity comes from how we define a galaxy. At one end, there are giant ellipticals with trillions of stars dominating clusters. At the other, there are faint dwarfs with only a few million stars, barely held together by gravity. At what point does a collection of stars become a galaxy
rather than just a cluster. Astronomers draw the line at gravitational binding. If the stars are bound together into a stable system, it is a galaxy. But even then, the boundary can be fuzzy. Some dwarfs are so faint that they blur the distinction. Others orbit larger galaxies as satellites, raising questions about whether to count them separately. The definition itself shapes the total. To bring this closer to human terms, think of the observable universe as a city seen from above at night. Each galaxy is like a street lamp, a cluster of lights shining in the darkness. Some are bright, some are faint. Some are close together, some stand alone. If you try to count every street lamp in the city, you could not do it directly from your vantage point. You would sample neighborhoods, estimate the density, and project. The number you arrive at would be enormous, but you would know it is still only an approximation. The real total might be higher, because some lamps are hidden behind buildings or too faint to see. The same is true for galaxies. The number 2 trillion is an estimate, a best guess based on the data we have. But it carries with it the knowledge that the universe may hold even more. There is also the question of what lies beyond the observable universe. Our horizon is set by the age of the cosmos and the speed of light. Beyond that, space almost certainly continues. If it does, then the number of galaxies beyond our horizon may be infinite.
In that case, asking how many galaxies there are is like asking how many grains of sand are on an endless beach. The answer is not a number, but a concept, more than we can ever count. The observable universe gives us a bubble within which we can estimate, but the full reality may extend far beyond, filled with galaxies we will never see. This perspective changes the nature of the question. When we ask how many galaxies there are, we're really asking how many we can observe, how many we can infer, how many fit within the bubble of a light that reaches us. That number, whether it is hundreds of billions or trillions, is already beyond comprehension. But the deeper truth is that the number does not matter as much as the scale it implies. To know that there are trillions of galaxies is to know that the universe is not just vast, but overflowing, filled to the brim with islands of light. Each one contains billions of stars.
Each one is a place where planets can form, where life might arise, where histories unfold. The number is not just a statistic, it is a measure of possibility. It is humbling to realize that our Milky Way is one among trillions. When we look up at the night sky, we see only the stars within our own galaxy. The other galaxies are too far away to appear as more than faint smudges. And yet, those smudges represent systems as large and complex as our own, multiplied across the sky by the trillions. The universe is not a sparse wilderness with a few scattered islands. It is a crowded archipelago, more populated than we can fathom. The spaces between may be vast, but the total number of galaxies ensures that the cosmos is alive with light. And still, there is something soothing about the fact that we do not know the exact number. The uncertainty is part of the mystery, part of the beauty. We can estimate, we can infer, we can push our instruments to their limits, but the universe will always hold more than we can count. To live within it is to accept that there are things we will never fully know, horizons we will never fully cross, numbers we will never fully pin down. And yet we can still glimpse enough to be eat, enough to understand that the universe is richer and fuller than any list could capture. So when we ask, how many galaxies are out there? The best answer is that there are more than we can see, more than we can count, more than we can imagine. Hundreds of billions at the least. Trillions by current estimates, perhaps infinitely many beyond our horizon. Each one an island of stars, each one a place, each one part of the cosmic web. The number is vast, but the meaning is simple. The universe is filled with galaxies, and we live inside one of them. That knowledge is enough to carry us forward. Enough to remind us of both our smallness and our belonging. Enough to let us rest in the wonder of it all. When we think about how many galaxies there are, and about the trillions of islands scattered across the cosmic ocean, it naturally leads to another question. How do we see them at all? And what limits how far we can look? The answer lies in light. Light is the messenger of the universe, carrying information across unimaginable distances. Every star, every galaxy, every explosion or flicker in the cosmos sends out light. And when some of that light reaches us, we can read it, measure it, and use it to glimpse places we will never visit. But light also sets the boundaries of our vision. Because it travels at a finite speed and because the universe has only existed for a finite time, there are edges to what we can see. To think about light and distance is to think about both the power of sight and the edges of sight, the horizons that define our cosmic view. The first thing to realize is that when we look into the sky, we are not seeing things as they are now, but as they were when their light began its journey. The moon we see is 1 second in the past. The sun is 8 minutes in the past. The nearest stars are years in the past. Andromeda is 2 million years in the past. The galaxies and deep fields imaged by the Hubble and James Webb telescopes are billions of years in the past. Looking outward is looking backward. Every star and galaxy is a time capsule. Its light, a record of history. When we gaze at the night sky, we are surrounded not just by space, but by time layered around us in concentric shells. This layering has a consequence. It means that the farther we look, the younger the universe appears. The nearest stars are in the present, but the galaxies billions of light years away show us what the cosmos looked like when it was still in its infancy. By collecting their light, we can reconstruct the history of the universe, tracing it back to its earlier stages. This is why telescopes that see farther are also telescopes that see earlier. The James Webb Space Telescope is powerful, not just because it can detect faint galaxies, but because those galaxies are so far away that their light left them billions of years ago, letting us witness the universe when it was less than 1 billion years old. Light also carries another signal, one created by the expansion of the universe. As space stretches, it stretches the light traveling through it, shifting it toward longer, redder wavelengths. This redshift is like a cosmic fingerprint of distance. The more distant a galaxy, the more its light is redshifted. By measuring the redshift of a galaxy's spectrum, astronomers can estimate how far away it is and how long its light has been traveling. This makes redshift one of the most important tools in cosmology, a way of turning light into distance,
of turning faint smudges into precise markers of the universe's expansion. But redshift also reveals a limit. Beyond a certain distance, the expansion stretches light so much that it slips beyond what our instruments can detect. This is why the James Webb Telescope works in infrared. The light from the earliest galaxies has been stretched out of the visible spectrum into the infrared. So only by detecting those longer wavelengths can we see them. Even so, there is a point beyond which the light is stretched so far that it can never be observed. The expansion carries galaxies away faster than their light can reach us, placing them permanently beyond our horizon. This is not because the light is too faint, but because space itself is expanding too quickly. The edges of sight are defined not just by the age of the universe, but by its motion.
Another edge comes from the cosmic microwave background, the afterglow of the Big Bang. This light comes from a time when the universe was only 380,000 years old, when it had cooled enough for atoms to form and light to travel freely. Before that, the cosmos was opaque, filled with a hot plasma that scattered photons endlessly. We cannot see beyond that moment with light, because there was no free light to see. The cosmic microwave background is a wall not of matter, but of opacity, the point at which sight itself begins. Beyond it, we can infer, simulate, and theorize, but we cannot observe with light. This is one of the most profound edges of sight, the horizon of the visible universe. The fact that light defines our vision also means that the observable universe is a bubble centered on us. This does not mean we're in a special place. It simply means that light reaches us from all directions out to the same limit.
Every observer, no matter where they are, has their own observable universe centered on them. Someone in a galaxy billions of light years away would also see a bubble around them with its own edges of sight. The universe is larger than any one bubble, but each observer's horizon is personal, defined by the light that has had time to arrive. This makes the cosmos both universal and local, both infinite in scope and finite in vision. It is worth pausing to consider how extraordinary this is. From a single planet, using light as our messenger, we can see billions of light years into the past. We can reconstruct the history of galaxies, clusters, and the universe itself. We can detect signals from when the cosmos was less than 1 million years old. We can measure redshifts that tell us how fast galaxies are receding. We can map the cosmic microwave background, seeing the universe as a glowing infant. Light is the bridge that connects us to all of this, and without it, we would know almost nothing about the cosmos. Our entire understanding of the universe rests on the fact that light travels, that it carries information, and that it can be read. And yet, light also humbles us. It shows us that there are limits we cannot pass. We cannot see beyond the microwave background. We cannot see galaxies whose light has not yet reached us. We cannot see objects carried away faster than light by the expansion of space. Our vision is bounded not by our imagination, but by the physics of light and time. The edges of sight are as real as the stars we see. They are horizons built into the structure of the universe. This interplay of power and limit is part of what makes astronomy so compelling. On one hand, we can see farther than any human before us imagined, glimpsing galaxies billions of light years away, mapping the structure of the cosmos, detecting signals from the dawn of time. On the other hand, we know that beyond our horizon lies more, unreachable, unseen, perhaps infinite. Light gives us both knowledge and mystery. It shows us what is and reminds us of what is hidden. For us standing under the night sky, this can be a source of comfort. Every star we see is light that has traveled across space to reach us. Every galaxy in a telescope is a time capsule, carrying its history to our eyes. The edges of sight remind us that the universe is larger than we can know. But they also remind us that we're connected to it by light. We're not separate from the cosmos. We're in it, part of it, seeing it with the only tool that matters, the light that shines across the dark. When we pause to think about light, distance, and the edges of sight, the picture that forms is already vast enough to overwhelm us.
Galaxies shining from billions of years in the past, their light stretched and reddened by the expansion of space, and a horizon that marks the farthest signals we can ever hope to see. Yet, the story does not stop there. If anything, that horizon is only the beginning of another question, one that reshapes how we think about the universe as a whole. What happens beyond that horizon? What does it mean that the universe is expanding? And why are there galaxies that we will never see? Not because they are too faint, but because they are being carried away from us faster than light itself can bridge the gap. To explore this is to sit with one of the most humbling truths of cosmology. Much of the universe is already and forever will be beyond our reach. The expansion of the universe is not a new idea, but its implications still surprise. In the 1920s, Edwin Hubble and others observed that distant galaxies are receding from us. Their light redshifted in proportion to their distance. The farther away a galaxy is, the faster it appears to be moving away. This discovery led to the realization that space itself is expanding. The galaxy is not flying apart like debris from an explosion. Instead, the very fabric of space is stretching, carrying galaxies with it. On small scales, gravity holds galaxies and clusters together. But on the larger scales, expansion dominates, pulling the cosmic web outward, enlarging the distances between filaments, walls, and voids. This stretching has a consequence that is easy to misunderstand, but profound once it settles in. Because space itself expands, galaxies far enough away are receding from us faster than the speed of light. This does not violate relativity because no galaxy is moving through space faster than light.
Rather, space itself is expanding, and in doing so, it increases the distance between us and those galaxies at a rate greater than light can cover. The result is that their light emitted today will never reach us. They are beyond our cosmic event horizon, not just unseen now, but unseeable forever. This event horizon is different from the horizon of the observable universe. The observable universe is defined by how far light has traveled since the Big Bang. The event horizon is defined by how far light will ever be able to travel in the future. Because the universe's expansion is accelerating, driven by dark energy, the event horizon is closer than the observable horizon. There are galaxies we can see now. Their light emitted billions of years ago, but we will never see them as they are today, because the light they are emitting now will never reach us. They are already receding too quickly. We see their ancient images, but their present and future are cut off from us forever. This is one of the strangest and most sobering aspects of the expanding universe. We live in a cosmos filled with galaxies, and yet the majority of them are already beyond reach. Over time, as expansion continues,
even more will slip beyond the event horizon. In tens of billions of years, galaxies outside our local group will fade from view entirely. Their light will be stretched until it becomes undetectable, leaving only the faint glow of our own cluster of galaxies. For any future observers, the universe will appear dark and empty, with no evidence of the cosmic web that we can see today. The knowledge we have now is, in a sense, a gift of timing. We live at a moment when the universe is still transparent enough, still filled with visible galaxies, still rich with signals to read. Far in the future, much of that richness will vanish from sight. This leads to a realization that is both unsettling and grounding. Our picture of the universe is temporary, not because the cosmos itself is changing too quickly, but because our view is limited by expansion. The edges of sight are not fixed. They move, receding as light arrives from farther away, but also shrinking in what is possible. As expansion pushes galaxies out of reach, it is as though we stand on a shore, watching ships drift across the horizon. Some ships arrive, their sails catching the light as they approach. Others, already too far, disappear into the haze, never to be seen again. The sea is full of ships, but only some pass through our line of sight. The rest sail into distances we cannot follow. The discovery of accelerated expansion in the 1990s made this picture even starker. Before that, astronomers debated whether the universe's expansion would continue forever, or eventually slow and reverse under the pull of gravity. The discovery that expansion is accelerating changed the question.
Now, it is not a matter of whether galaxies will keep drifting apart, but how quickly they will slip beyond reach.
The driver of this acceleration is dark energy, a mysterious component of the universe that makes up about 70% of its total energy density. We do not know what dark energy is, only that it acts as a kind of negative pressure, pushing space apart. Its presence ensures that expansion will not only continue, but accelerate, making the event horizon an unavoidable feature of our future. To live in an expanding universe is to live with horizons, the observable horizon defined by the age of the cosmos. The event horizon defined by the acceleration of expansion. These horizons are reminders that we are not at the center, not privileged, but simply limited by physics. The light we see is the light that has had time to arrive. The galaxies we will never see are not hidden by choice, but carried away by the universe's own growth. The cosmos is not infinite in our perception, even if it is infinite in reality. It is bounded by the speed of light and the stretch of space. And yet, this limitation is not cause for despair. It is part of what makes our current view so precious. To know that galaxies are slipping away is to know that we live in a rare era of cosmic clarity. When the sky still holds evidence of the Big Bang, when the cosmic web is still visible, when the universe still reveals its history and light, future observers, trillions of years from now, will not see what we see. They will live in a dark universe with only their local galaxies visible, with no microwave background to study, with no expansion to detect. For them, the universe will appear static, isolated, small. Only now, in this narrow window, is the universe transparent enough and young enough to show us its full story. This thought makes our moment in cosmic history feel both fleeting and extraordinary. It also reframes how we think about distance. When we say a galaxy is a billion light-years away, we're describing not just how far its light has traveled, but also how expansion has reshaped that distance. In fact, the galaxy is now much farther away than the distance implied by its light travel time, because space has stretched in the meantime. This is why cosmology often distinguishes between light travel distance, co-moving distance, and proper distance. Each tells a different part of the story. The numbers can feel abstract, but the point is simple. Distance in an expanding universe is not fixed. It grows. It stretches. It carries galaxies outward, sometimes beyond reach altogether. To sit with this thought is to accept that the universe is not a place we can map fully. It is a place we can glimpse, describe, estimate, but never hold in its entirety. The expansion ensures that some parts are always beyond us, some light never to arrive, some galaxies forever unseen.
Our maps are partial, our knowledge bounded, our horizons inevitable. But within those bounds, the view is astonishing. We can see billions of galaxies, trace billions of years, glimpse the afterglow of creation. We can measure the rate of expansion, detect the presence of dark energy, and describe the cosmic web. Even if much lies beyond, what lies within is enough to fill us with wonder. The thought of galaxies slipping away can feel lonely, as though the universe is emptying out around us. But there is another way to see it. The galaxies not leaving us. We're all carried by the same expansion, all part of the same fabric. The universe is not scattering us apart, but stretching itself evenly. We remain connected by the history we share, by the light that has already left, by the story written in the sky. The ships on the horizon may disappear, but their trails remain in the waves. Their signals remain in the light we catch.
The universe expanding beyond reach does not erase what is. It only sets the boundaries of what will be. So when we think about the universe expanding beyond reach, we are really thinking about time, about perspective, about the balance between what we can know and what we cannot. The observable universe shows us the past. The event horizon defines the limits of the future. Between them lies our present, a moment when galaxies still shine, still send their messages, still remind us of the immensity beyond. To live in this moment is to live in a rare window of cosmic clarity, a time when the universe is still open, still full, still visible. And even as expansion carries most of it beyond our reach, the part we can see is enough to remind us that we belong to something vast, mysterious, and beautiful. When we think about the universe expanding beyond reach, with galaxies carried away faster than light can bridge the gap, another thought naturally follows. Why is the universe so much bigger than our galaxy in the first place? Why do we live in a cosmos that stretches 93 billion light-years across, when the Milky Way itself is only 100,000 light-year wide? The difference in scale is staggering. The Milky Way is already vast beyond human comprehension, but compared to the universe, it is a grain of sand on an endless beach. To ask why the universe is so much bigger than our galaxy is to ask about history, about physics, and about the processes that shaped both small and large scales. It is not a question with a single answer, but rather a set of reasons that together explain the immense contrast.
The first and most fundamental reason is the origin of the universe itself. The universe began in the Big Bang, not an explosion in space, but an expansion of space itself. From a hot, dense beginning, the universe expanded and cooled, creating the conditions for matter to form, for atoms to appear, for light to travel. That expansion has continued for 13.88 billion years. On such timescales, even modest expansion becomes immense. And because space has been stretching all the while, the universe has grown to sizes far larger than any individual structure within it. Galaxies formed inside this expanding space, but they are small compared to the whole localized concentrations of matter in a vast, ever-growing fabric. Another reason lies in how matter clumped after the Big Bang. In the early universe, matter was spread almost uniformly, with tiny fluctuations in density. Gravity amplified those fluctuations, pulling matter into denser regions where galaxies and clusters would eventually form. But the scale of those clumps was limited by the physics of the early cosmos. Galaxies could only grow so large before their own gravity stabilized them. Beyond that scale, gravity continued to act, but it pulled galaxies into clusters and superclusters rather than into single structures.
The universe is larger than any galaxy, because galaxies are only one level of structure shaped by limits of physics, while the universe itself is not bounded in the same way. Dark matter also plays a role. Galaxies are held together by the gravity of dark matter halos, invisible structures that outweigh the stars by a factor of 5 or more. These halos define the maximum size of a galaxy because beyond their reach, matter is no longer bound to the system. The Milky Way's dark matter halo may extend several 100,000 light years, but that is still tiny compared to the universe. The scale of galaxies is determined by the reach of their halos. The scale of the universe is determined by the age of expansion. The two are governed by different processes, and the result is a difference in scale so large it resists direct comparison. There is also the fact that galaxies are not solitary. They are part of larger structures linked into the cosmic web. Our galaxy belongs to the local group, which belongs to the Virgo cluster, which belongs to the Lania supercluster. Each level of structure extends the scale upward, until finally we are mapping the observable universe itself. In this sense, asking why the universe is so much bigger than a galaxy is like asking why the ocean is so much bigger than a wave. The wave is part of the ocean, shaped by it, contained within it. The galaxy is part of the universe, shaped by it, contained within it. The difference is not arbitrary, but intrinsic to the relationship between part and whole. Time must also be considered. The universe has had nearly 14 billion years to expand, to cool, to form structure. Galaxies, by contrast, formed only a few 100 million years after the Big Bang and have been evolving ever since. They're younger than the universe, smaller because they are products of its physics. If the universe had existed only a short time, galaxies might not yet have formed, or they might be smaller still. It is the long history of expansion that makes the universe so vast, while the more limited processes of gravitational collapse define the size of galaxies. Another way to see the difference is to think about what galaxies are made of. Galaxies are concentrations of matter, stars, and gas bound by gravity. The universe is not a single bound system.
It is the stage on which all galaxies exist, the fabric of space-time itself. The size of a galaxy is determined by balance, gravity pulling inward, motion resisting collapse. The size of the universe is determined by expansion, space stretching outward without limit. One is bound, one is unbound. One is local, one is global. Their scales are different because their natures are different. It is easy to imagine asking why galaxies cannot be as large as the universe itself.
Why not one galaxy filling all of space, rather than trillions of smaller ones? The answer lies again in physics. If matter had clumped into a single system, there would be no room for diversity. No stars spread across countless galaxies, no cosmic web. Instead, the slight unevenness of the early universe ensured that matter collapsed into many smaller systems rather than one overwhelming whole. Galaxies are the natural scale of structure. The universe is the natural scale of existence. The difference in size is what allows the richness we see today. The variety of galaxies, the networks of clusters, the patterns of voids. This contrast is also a matter of perspective. From our point of view, the Milky Way feels immense. 100,000 light-years is far beyond our ability to traverse. The nearest star system, Proxima Centauri, is more than 4 light-years away, already beyond reach with current technology. To us, the galaxy is more than enough, more than we can explore.
But from the perspective of the universe, the Milky Way is small. One island among trillions, one wave among countless others. Scale is relative, and the difference between galaxy and universe reminds us that our sense of size depends on where we stand. The sheer immensity of the universe compared to the Milky Way also carries philosophical weight. It suggests that our galaxy, though vast to us, is not the measure of all things. It is part of a much larger whole, one we can glimpse but never fully contain. This does not make the Milky Way less meaningful. It makes it more precious because it is our home, our island in the sea, our wave in the ocean. The fact that the universe is so much larger does not diminish the galaxy. It gives it context, showing us that we live not in isolation, but in connection, part of something vast beyond measure. This context also opens possibilities. If there are trillions of galaxies, each with billions of stars, then the potential for planets and life is multiplied beyond imagining. The fact that the universe is so much bigger than our galaxy is not just a fact of scale, it is a fact of possibility. It means that the story of existence is not confined to one system, but spread across countless others. It means that the potential for discovery, for wonder, for meaning is multiplied by trillions. The universe is larger because it holds more. The galaxy is smaller because it is one chapter in a much larger book. So when we ask why the universe is so much bigger than our galaxy, the answer is layered. Because expansion has been at work for billions of years. Because galaxies are limited by physics. Because structure forms hierarchically. From stars to galaxies to clusters to superclusters to the universe itself. Because matter clumps on small scales but spreads on large ones. Because the universe is the fabric and galaxies are the patterns woven into it.
The difference in size is not a flaw or an accident. It is the natural result of how the cosmos works.
The Milky Way is small compared to the universe, but it is vast compared to us. The universe is large compared to the Milky Way, but it is still something we can glimpse, measure, and describe. Scale is relative, and meaning is not measured by size. The Milky Way is our home. The universe is our context. To know both is to know ourselves more fully, to rest in the balance between smallness and belonging, between part and whole, between the galaxy we live in and the universe that holds it. When we reflect on why the universe is so much bigger than our galaxy, the numbers and comparisons can easily feel overwhelming. 93 billion light-years across, 2 trillion galaxies within sight, trillions upon trillions of stars, scattered across a cosmic web that stretches farther than light has had time to travel. Against that backdrop, the Milky Way is a small island. Against the Milky Way, Earth is a speck, and against Earth, each of us is a fleeting presence. To sit with this knowledge is to confront not only scale, but meaning. What does this vastness mean for us? What should we take from the recognition that the cosmos is so much larger than our home, and so much older than our lives? The first response many people feel is humility. When you stand beneath a clear night sky, especially far from city lights, the sheer number of stars can already make you feel small. Add to that the understanding that every star is only one among hundreds of billions in our galaxy, and that our galaxy is one among trillions in the universe, and the sense of smallness deepens.
We are tiny in comparison, temporary against billions of years, fragile in the face of cosmic immensity. For some, this humility feels like insignificance, a reminder that our struggles and ambitions are vanishingly small against the universe. But for others, humility opens into perspective. To be small is not to be meaningless. It is to be part of something larger than ourselves. A whole so vast, it cannot be contained in numbers alone. This perspective can shift how we see our lives. The problems of daily existence, frustrations, deadlines, disappointments, can shrink when viewed against the cosmic scale. They do not disappear, but they take on a new proportion. To realize that galaxies are slipping beyond reach, that stars are being born and dying across billions of light years, is to remember that our own concerns are not the whole story. We are participants in a universe far larger than our individual selves. And sometimes, that reminder can bring calm.
It can soften the edges of urgency and open space for gratitude. The vastness also inspires wonder. To know that there are trillions of galaxies is to know that the universe is not just large, but abundant. It is overflowing with light, with stars, with potential. Every galaxy contains billions of suns. Many of those suns likely have planets. Some of those planets may have conditions where life could emerge. The vastness multiplies possibility, making it difficult to imagine that we are the only conscious beings in existence. This thought can be exhilarating, a reminder that the universe may be alive with stories beyond our own, even if we never encounter them. The immensity becomes not emptiness, but promise. At the same time, the vastness emphasizes fragility. Earth is small, delicate, and alone in a wide ocean of dark. The conditions that make life possible are narrow. The right distance from the sun, the right mix of atmosphere, the right history of geology and chemistry. Against the universe, our planet is a rare haven. Recognizing this can deepen our sense of responsibility. If the universe is filled with galaxies, but life is rare, then the life on Earth is precious beyond measure. The vastness becomes a mirror, showing us that our world is not disposable, that our survival is not guaranteed, and that our choices matter. The immensity also raises philosophical questions. If the universe is so much larger than our galaxy, what is our role within it? Are we a random byproduct of physics? Or are we part of a pattern that repeats elsewhere? Is our consciousness a rare flicker in a dark cosmos, or one of countless lights? The vastness does not answer these questions, but it frames them, making them more poignant. To be aware of the universe at all is remarkable. Galaxies do not know themselves. Stars do not reflect on their size. But we can. Somehow, a species on a small planet orbiting an ordinary star in a typical galaxy has gained the ability to measure the cosmos and ask what it means. That ability is itself extraordinary, and it may be the meaning we bring to the vastness. Another way to approach the question is through connection. Though the universe is larger than we can comprehend, we are not separate from it. We are made of the same elements forged in stars, the same atoms born in the Big Bang. Every atom in your body, every breath you take, every thought you think is part of the cosmos. You're not outside it, looking in. You're inside it, woven into it, a product of it. The vastness is not something alien. It is home. To realize this is to shift from seeing ourselves as small strangers in a giant universe to seeing ourselves as small parts of a single whole. The vastness means we belong, not because we're large, but because we are inseparable. For some, this thought is deeply comforting.
It means that even though our lives are brief, even though our scale is tiny, we are not isolated. We are expressions of the universe itself, temporary gatherings of atoms that were once in stars and will one day return to them. Our consciousness is a momentary way for the cosmos to know itself. When we look at the night sky, we are not looking at something other. We are the universe looking at itself, recognizing its own vastness. This does not make us less. It makes us extraordinary, precisely because we can know it. The vastness also shapes how we imagine the future. On human scales, we think in years and centuries. On cosmic scales, stars live for billions of years. Galaxies merge over eons. The universe itself will expand for trillions. Against this backdrop, our moment is brief, but it is also unique. We live at a time when the universe is still visible, when the cosmic microwave background can still be detected, when galaxies can still be mapped. Far in the future, much of this will fade beyond reach, carried away by expansion. Our moment is one of rare clarity, and the vastness makes that clarity feel like a gift. It reminds us that knowledge itself is fleeting, that what we see now is not eternal, and that our time to know the universe in this way is limited. For many, the vastness also changes the way we think about meaning. It can feel as though scale threatens significance, as though being small makes us unimportant. But scale is not the measure of meaning. A poem is not less valuable because it is shorter than a novel. A life is not less meaningful because it is brief compared to the age of the universe. The vastness reframes meaning,
shifting it from size to presence. We matter not because we are large, but because we are here, now, capable of awareness, capable of care. The universe is vast, but our experience of it is intimate. That intimacy gives the vastness its significance. It is also worth considering how the vastness shapes our relationships with one another. When we recognize that we all live on the same small planet, in the same small galaxy, the divisions we create, nations, borders, conflicts, can appear smaller too. They do not vanish, but they can be softened by perspective. Against trillions of galaxies, our differences are trivial. Against billions of years, our disputes are brief. The vastness does not solve problems, but it invites us to see them in proportion, to remember that we share a fragile world in a vast cosmos, and that cooperation may matter more than division. So what does the vastness mean for us? It means humility because we are small. It means perspective because our concerns are temporary. It means wonder because the universe is abundant. It means responsibility because our world is fragile. It means connection because we are made of the same matter as the stars. It means gratitude because we live at a rare moment when the cosmos is still visible. And it means possibility because the universe is larger than we can imagine. And within it, there may be more stories than we will ever know. As we let this settle, the vastness becomes less intimidating and more soothing. It does not erase us, it embraces us. It tells us that we are part of something greater, and that our small-ness is not a flaw, but a truth. To live in a vast universe is to live with perspective, with humility, with awe. It is to remember that we belong to a cosmos that stretches beyond reach, and that belonging itself is enough. After sitting with the idea of what the vastness means for us, the question turns naturally toward our place within it. If the universe contains trillions of galaxies, if the Milky Way is just one island among countless others, and if the observable universe is 93 billion light-years across, then what does it mean to be human in such a sea of galaxies? The image is both humbling and arresting. We are small, undeniably so. We are fleeting, living for decades against billions of years. And yet, here we are, able to reflect, able to measure, able to ask. To think of our place is not only to confront our scale, but to consider what it means that we are aware of it at all. The first layer of our place is physical. We live on a small planet orbiting an ordinary star about halfway along one spiral arm of the Milky Way. Our galaxy has hundreds of billions of stars, and we're not near its center, nor near its edge, but in a middle region, often called the Orion Arm or the Orion Spur. Around us, stars are scattered in every direction, each with its own system, many with planets of their own. From here, the Milky Way appears as a pale band across the night sky, a reminder that we are inside it, part of it, surrounded by it. Physically, our place is modest, a speck in a spiral, one among billions of stars. But even within that modesty, there is a sense of belonging. We are not outside looking in. We're inside, woven into the fabric of a galaxy that itself is woven into the fabric of the universe. The second layer of our place is temporal. The universe is 13.8 billion years old.
The Earth formed about 4.5 billion years ago. Humans, as a species, have existed for a few 100,000 years. Modern civilization spans only a few thousand. Against this backdrop, our time is short. The galaxies we see have been evolving for billions of years. Many of them will continue to exist for billions more, long after our species is past. Our moment is brief, but it is also unique. We live at a time when the universe is still visible in its richness,
When galaxies are still shining, when the cosmic microwave background can still be detected, when expansion can still be measured. Our place in time is as significant as our place in space. We exist in a narrow window when the cosmos is transparent enough to reveal itself. That window will not last forever, and the knowledge we hold now is part of what makes our moment precious. The third layer is cognitive. We are not the largest beings in the universe, nor the longest lived, nor the most powerful. But we are among the few who can ask questions about the universe at all. As far as we know, galaxies do not reflect on their size. Stars do not contemplate their fusion. Planets do not ask what lies beyond their horizons. But we do. Our minds have grown to the point where we can measure the universe, map it, describe it, and wonder about it. That capacity is extraordinary. It places us in a role not of size or power, but of awareness.
The sea of galaxies is vast, but our awareness of it gives it meaning. In that sense, our place is not only physical or temporal, but conscious. We are participants who can know the ocean we float in. Our place is also relational. To be human is not to exist alone, but in connection with one another, with our planet, with our galaxy, and with the universe itself. The atoms in our bodies were forged in stars. The oxygen we breathe, the iron in our blood, the calcium in our bones, the carbon in our cells, all were created in stellar furnaces and scattered by supernova. We are star stuff, as Carl Sagan once said. But more than that, we are universe stuff. The very laws that govern galaxies govern us. The very expansion that carries galaxies apart carries us too. Our place is not separate from the cosmos, it is continuous with it. To recognize this is to feel a deep sense of connection, a belonging that transcends scale. Yet another aspect of our place lies in perspective.
When we look outward and see the sea of galaxies, we do not only learn about them, we also learn about ourselves. The vastness can make us feel small, but it can also make us see that meaning does not depend on size. A galaxy is not meaningful because it is large. It is meaningful because it is part of the universe. Because it exists, because it contributes to the whole. By the same measure, we are meaningful not because we are vast, but because we are here, part of the same whole. The sea of galaxies does not erase us, it situates us. Some people respond to this perspective with awe, others with unease. Awe, because the scale is breathtaking, and to know it is to feel part of something magnificent. Unease, because smallness can feel like insignificance. But unease can soften when we remember that awareness itself is rare. Among the trillions of galaxies, among the countless stars and planets, we do not yet know how common consciousness is. Perhaps it is widespread, perhaps it is rare. Perhaps we are among the few places in the cosmos where the universe looks at itself. If so, then our place is not insignificant at all. It is extraordinary, not because of size, but because of awareness. There's also a moral dimension to our place. To know that we live in a fragile world on a small planet in a vast sea of galaxies is to feel responsibility. The Earth is our only home. It is rare, delicate, and precious. Against the backdrop of the universe, it is irreplaceable. Our place includes the duty to care for it, to recognize that while the cosmos is vast, our world is not disposable. The sea of galaxies may be endless, but our home is singular. To neglect it would be to forget our place entirely. The vastness reminds us not only of humility and wonder, but of responsibility and care. Our place is also dynamic. The universe is not static, and neither are we. The Milky Way is moving, drifting toward Andromeda. Galaxies merge, clusters form, superclusters flow along cosmic highways. We too are in motion, carried by the same currents, evolving as part of the same history. Our place is not fixed. It is a moment in a moving story, a chapter in a cosmic narrative. To understand that is to see that our place is both humble and grand. Humble because we are not the center. Grand because we are participants in the unfolding of the universe itself. It is tempting to ask whether the sea of galaxies cares about us. The answer is no, at least not in the sense of intention or design. The cosmos is indifferent. Galaxies form and dissolve without regard for our existence. Stars burn and die whether or not we notice. The expansion continues whether or not we measure it. But our awareness gives the cosmos a kind of reflection it would otherwise lack. The sea of galaxies may not care, but we do. We bring meaning by recognizing it, by caring about it, by situating ourselves within it. Our place is not given by the universe, it is made by our awareness of the universe. And so, what is the human place in a sea of galaxies? It is small, fragile, and fleeting. It is also conscious, connected, and extraordinary. We are not the rulers of the cosmos, nor its center, nor its largest inhabitants. We are a species on a planet in a spiral arm of one galaxy among trillions. But we are also the universe made aware of itself, a way for the cosmos to look inward and ask what it is. Our place is not to control the sea of galaxies, but to know it, to marvel at it, to reflect on it. In that sense, our place is as meaningful as any galaxy, because it is through awareness that the sea becomes not only vast, but wondrous. As we let this settle, the image of the Sea of Galaxies changes. It is no longer just an ocean in which we are adrift. It is an ocean we are part of, one whose waters flow through us, one whose waves we ride, one whose story we tell. Our place is small, but it is real. Our place is fleeting, but it is ours. Our place is not the whole story, but it is a chapter, and that is enough. To know this is to rest more easily in the vastness, to see the Sea of Galaxies not as something that diminishes us, but as something that holds us, surrounds us, and connects us to everything that is. After reflecting on our place in a sea of galaxies, the journey feels as though it is drawing to a natural pause. We have traveled from the scale of our home star system to the farthest edge of the observable universe. We have thought about the Milky Way as an island of light, counted the stars within it, traced the gaps between galaxies, followed the highways of clusters and superclusters, measured the immeasurable with light as our tool, and finally compared the whole of the universe with the single galaxy that we call home. At each step, the scale has grown, and with it, our sense of perspective has deepened.
But now, as we arrive at the end of this journey, there is space for something quieter, something more personal. The question is no longer about numbers or measurements, not about why the universe is so much bigger than our galaxy, but about how we rest with that knowledge. What does it feel like to sit beneath the infinite, knowing what we now know? The first feeling is one of when you learn just how vast the universe is, how small our galaxy is within it, and how tiny our planet is compared to even the galaxy. There comes a moment when the need to grasp it all falls away. The numbers are too large to hold in the mind all at once. 93 billion light years, 2 trillion galaxies, a septillion stars. Beyond that, perhaps infinity. These are not statistics we can carry like items in a pocket. They are realities that exceed our capacity. And so, instead of trying to hold them tightly, we can rest in their immensity. We can let them wash over us, like lying back on a beach and hearing the waves, knowing the ocean is larger than we will ever cross, but feeling comfort in its sound and presence. The infinite cannot be possessed. It can only be experienced in glimpses, and that is enough. Another feeling is perspective. Beneath the infinite, our own struggles and anxieties can soften. This does not mean they vanish. Our lives are still real, still precious, still immediate. But the vastness reframes them, placing them in a larger context. The deadlines, the arguments, the disappointments shrink when seen against billions of years and light years. This does not make them unimportant, but it makes them less absolute. Beneath the infinite, the sharpness of daily life is dulled by perspective, and in its place comes a sense of proportion, even a sense of calm. The universe is vast, but it is also steady. Stars are born and die. Galaxies drift and merge. Space expands. And yet, through it all, there is continuity. To rest beneath the infinite is to feel part of something stable, even as our own lives shift from moment to moment. There is also a sense of belonging. At first, the infinite can make us feel small, even insignificant. But the more we think about it, the more it becomes clear that we are not outside it. We are inside it, made of it, connected to it. The atoms in our bodies were forged in stars. The elements we breathe, drink, and eat were created by the same processes that shape galaxies. We're not intruders in the cosmos. We are the cosmos, temporarily arranged in human form, aware enough to notice itself. Resting beneath the infinite means remembering that we're not separate from it, not strangers looking in, but participants within it. The infinite is not something above us. It is something we are part of, inseparable and continuous.
This belonging carries with it comfort. To know that we are part of something vast is to know that we're not alone, even when we feel isolated. The sea of galaxies is filled with light, and while we may never touch those other islands, their presence is reassuring. They shine across the darkness, remind us that the universe is not empty, but full. The infinite is not void. It is abundance, overflowing with stars, planets, and possibilities. To rest beneath it is to feel surrounded, not by silence, but by presence. The night sky becomes a blanket, not a void, covering us with its patterns and its depth. There is another layer, one that is quieter, but no less important. Resting beneath the infinite is an act of acceptance. The universe contains mysteries we will never solve, horizons we will never cross, distances we will never bridge. There will always be questions without answers, always regions beyond our reach, always aspects of reality hidden from us.
At first, this can feel frustrating, as though knowledge must be complete to be meaningful. But acceptance brings peace. We do not need to know everything to belong. We do not need to see beyond the horizon to rest within it. The infinite is not diminished by mystery. If anything, the mystery is what makes it infinite. To rest beneath it is to accept that not knowing is part of the experience, that wonder is made richer by questions that remain open. Another aspect of rest comes from time. Our lives are brief, and that brevity can sometimes feel heavy. But beneath the infinite, time stretches in both directions. Stars live for billions of years. Galaxies evolve over eons. The universe itself has been expanding for nearly 14 billion years and may continue for trillions more. Against that backdrop, our own years and decades seem small, but they are not without meaning. They are moments within a larger story, brief flashes of awareness in a long unfolding.
Resting beneath the infinite means releasing the need for permanence and instead embracing the value of the present moment. A single star does not need to shine forever to have meaning. It matters simply because it shines at all. And the same is true for us. The infinite also invites a sense of gratitude. To be alive, to be conscious, to look up at the night sky and think about galaxies and the universe. That is extraordinary. The odds of existing at this moment, in this place, with this awareness, are unimaginably small. And yet, here we are. Gratitude doesn't remove hardship, but it softens it. It brings a sense of balance beneath the infinite. Gratitude arises naturally when we recognize how rare and fragile life is, how brief our window of awareness is, how fleeting our chance to reflect on the cosmos truly is. Gratitude transforms vastness from something overwhelming into something sustaining. And perhaps most of all, resting beneath the infinite brings peace. Not because the universe itself is gentle. It is filled with violent processes, from supernovae to black holes. But because its scale is steadying, the stars will continue to rise and set. Galaxies will drift and merge. Expansion will carry on. None of this depends on us. And none of it is threatened by us. In a world where so much feels uncertain, the cosmos offers a kind of reassurance. It continues vast and steady, and we are part of it. To rest beneath the infinite is to feel carried by it, not in control, but not excluded. A passenger on a journey across time and space. So what does it mean in the end to rest beneath the infinite? It means release from the need to hold it all. It means perspective on our lives. It means belonging to something larger. It means comfort in presence, acceptance of mystery, gratitude for awareness, and peace in scale. It means seeing the night sky not as something distant, but as something intimate, not as a void, but as a home.
The infinite is not a place we will one day reach. It is the place we already inhabit, the reality we are already part of, the blanket under which we already rest. And with that, the journey that began with a greeting beneath the stars and moved outward through galaxies, clusters, and the observable universe circles back to where it began, the human experience of the night sky. We are still here, still beneath it, still listening to the silence of space and the whispers of light. The infinite stretches beyond us, and yet it holds us. To rest beneath it is not to end the journey, but to settle into it, knowing that the cosmos is vast, that we are small, and that the combination of those two truths is what makes the night so profoundly calming. And so, as we let these thoughts settle, the universe continues above us, vast and steady, carrying on whether we are watching or not. The galaxies remain. The stars continue to shine. The space between stretches quietly onward.
We do not need to hold all of it at once. We only need to remember that we are part of it, that we belong to it, and that it belongs to us. If you found comfort in drifting through these reflections, you might enjoy resting with us again. You can always return to this space where curiosity meets calm, where science becomes a companion for sleep. If you'd like to hear more journeys like this, you can follow along or share this moment with someone who might need it too. For now, simply let your breathing slow, let your body rest, and let the vastness of the night sky hold you. The galaxies will be there tomorrow, and the universe will always be waiting. Good night.